Good morning and welcome back to day 3. Today we are going to have an exciting agenda. We're going to talk a lot about data and trust. If we want to go, well, our first speaker, we should start with introducing
Good morning and welcome back to day 3.
I'm sorry, I think my apologies. I was live streaming in the background to keep an eye on the Slido and I forgot to mute it. I'm very sorry about that. We will start that over again. I would like to start the day with our 4 speakers introducing themselves, although I think you have seen 2 of us several of the days, and Andrea. I just want to do a brief, quick introduction of the 4 of us. So I'm Amy McGovern. I'm the director for TAI4ES.
I'm Chris Wares. I'm a postdoc on the risk communication team for TAI4ES.
I'm Andrea Schumacher. I'm a researcher with Colorado State and CIRA, and I work with the TAI4ES RiskCom group.
I'm doctoral research scientist with Corporate Institute for Satellite and Earth System Studies with NOAA Center for Artificial Intelligence.
Excellent. Next slide. You're going to be hearing from all of us, and we're going to be switching back and forth. And so it was easier to do all the introductions right up front than doing it every time we switch back and forth. The goals of what we're going to do today, we are going to work on teaching you about the importance of trustworthy data and how much the data really matters to everything we're doing. I think it's something that we don't talk about enough. We spend a lot of time the last 2 days talking about how to look inside the methods and how to peer inside the black box. But the saying is garbage in, garbage out. If we give it crappy data, it's not going to give you any great models, right? They're not going to be trustworthy. So we need to talk about a lot of the aspects of what makes the data trustworthy, and also the workflow and how that can be made trustworthy. And then the second half of the day, we're going to talk about case studies and why case studies are useful and how they can relate to trust. Next slide. So we're going to do this slightly differently than the previous few days where we've been having lots more breaks. What we're going to do today is have 2 longer sessions with 1 15-minute break in the middle of the day. So we're starting off with trustworthiness of data and workflows, and then we'll have a brain and a bio break, and then we'll have another longer session at the end of the day on case studies. Next slide. Oh, I guess I should have left it on that slide to say, I should go back 1 slide, just 1 second. Just to say thank you to all of our sponsors who have helped make this summer school possible and are all on our slides here. Next slide now. And I believe I'm going to turn it over to Chris to get you all warmed up.
Yeah, so just like we did yesterday, going over to Slido and answering a quick warm-up question. So just to get the juices flowing, what words/phrases would you use to describe explainable AI? So we'll launch that first poll, 3.1, to kick off the day. Although you don't really need help with Slido. You've been pretty impressive as far as getting questions in there and good discussions. And we're doing our best to respond to them. There's a few from yesterday that we just replied to today. Some people hopped on. So if you have an answer or a question that you put out there, I think we're trying to leave about 30 minutes for you to see the reply. But also if you didn't see it and we archived it, your own personal archive, so the questions you asked should still be visible to you. Which is a note. All right, so here's our words for explainable AI. Transparent, a big one. Okay, nice. Inside the black box, robust, post hoc. Visually communicative, easy, applicable. All right, nice. Transparent, staying huge. That's great. That'll be a key one to keep in mind for today too when we think about workflow. So that's awesome. Cross-implementable. Post hoc explanations getting bigger. More people jumping on that. Reasonings explained. All right. Simplicity is coming in too. That's an easy one. Post hoc explanation. Okay, so we're kind of getting that difference between interpretable and explainable. You can see that post hoc is really coming back in. So people are paying attention yesterday, so that's great. Nice white box. Awesome. Using methods outside the model, right? So we apply something else to it. We got verification. Okay. Great. So we're picking up on a lot of those big themes from yesterday for sure. All right. And so that's a good warm up. Looks like people are doing a good job. We got one more, an easy kind of low hanging fruit question. So we'll switch to 3.2 here, which is going to be what was your favorite part of yesterday's lectures? So thinking about, okay, what did you like from yesterday? What kind of stands out to you when we think of what we heard yesterday? Favorite part of yesterday's lecture? Okay, getting the XAI for deep learning. Good. Interpretability, great. Digging into some of those ideas. Thinking about the difference of the terms. There's interesting discussions in Slido yesterday on that. I hadn't thought about the difference of these terms and what they mean. Risk-com, woo! I always love that. It's great to see as a risk-com scientist. Sensitivity and attribution, awesome. Yeah, neural networks, SHAP XAI, sensitivity versus attribution. Y'all were getting great detail on that and asking really good questions. The heat maps, excellent. Sensitivity versus, okay, explainable, interpretable. The case study for severe, yeah, so Rainey's got those great tutorials that are out and you can dig into. And for those of you in the Trustathon, it's one of the data sets you can play with. SHAP, okay, SHAP XAI is taken off, that's awesome. I also got the good resources from Evan and some insights in the chat on that. Q&A was pretty active. Yeah, it is definitely the place to be is Slido. As we can see, you all are doing awesome. Okay, we have a lot of good things here. Reproducibility, XAI, SHAP. Okay, people from yesterday, the speakers are going to be thrilled that you're paying us close attention and enjoyed it so much. All right, so I'll let this kind of taper off and we'll go back to the slides, and I'm just going to do a little bit of a framing and introduction on where we're headed. So we're talking about data sets and workflow, and we're thinking about trustworthiness in this process. So if you hit the next slide, I'm going to remind you what we talked about on the first day. So how we're defining trustworthiness here is, this is an evaluation that the truster, so the person that's deciding whether or not to trust, that they have. This is an evaluation perception, and they're thinking about whether, when, or why, or I guess really kind of how much. So the what degree someone or something should be trusted or not trusted, right? So you have a user's perspective, and we've often talked about it as it's shown in this box down in the bottom right-hand corner. So we think about a user perceiving the output or a specific model as being trustworthy or not, and that's the relationship we're looking at. But there are a lot of kind of upstream implications for this. So if you hit the next slide, this also relates to the way the model is developed, right? So we're thinking that our development decisions are going to impact our model output, which is also going to impact trustworthiness. If you hit this next slide again, there's a lot that goes into that development process too, as you all know, especially if you're doing the Trustathon, like even just getting your data fired up and everything and into being able to be run took a lot of time and a lot of thought. You had to make a lot of decisions. And so you can see things like the actual data, how the data is processed are going to impact that model development process as well as the output. But then that also has different implications along the lines of the code or software that you're using, the type of computing you're doing or the validation that you're running. So you hit the next slide. And then even before you get to this part of the process, even further upstream, you have things like the quality of your data, how the data was collected, the coverage of your data, and then the sampling. And so hit the slide one more time. All of these decisions that we make and have to think about and make kind of trade-offs and discussions for are opening room for potential error. So all these decisions that we're making also could lead to potential bias. So thinking about this whole process, it's really important not just to think about trust and trustworthiness with the output, but along this whole process, because a lot of these different points that we're doing have some subjectivity and room for error in them. So if you hit the next slide, we're really going to talk about this whole process. And the trust and trustworthiness from the user's perspective should cover all of these things. Because the output could be solid, but if the data isn't great, or there are problems, or there's kind of bias that's worked into it or error upstream, that's also going to impact whether or not someone should or should not trust something, or potentially how they perceive the model overall. Because this is really what we're going to hit on today, is covering the impacts of all these kind of upstream topics, and then thinking about how we really dig into understanding the user's perception throughout the process, and with the user's perception of all these different points, not just with one output. And so I can hit the next slide, and I think Douglas takes over from here.
Thanks, Chris, for this really nice framing of why we are talking about data right now. So first of all, when we're talking about data, we want to make sure that we understand the data source we use, both as a developer for an AI or machine learning model, or as a user who are using some of the AI applications. You want to know where the data is coming from. Is that coming from authoritative source or it's coming from a crowdsourced like data sets. So here we separate them into 3 different categories. One is the observational data, and the second one is the simulated and synthetic data. And the last one is the crowdsourced data, which has been used more and more in training and developing a model. And so AI in environmental observations in applications often use this 3 types of data and oftentimes combine them together in a lot of applications. So we're going to go through each different categories one by one. So first of all, let's looking at observational data set. So observational data set, one common data source is coming from the in situ measurements, which can come from station measurements from both the land and ocean. So here on the right side is an example of the station density of how many stations are measuring the precipitation from the global precipitation climatology data center. And for each, on this map, you can see there's a wide density disparity across the world, where in the North America, we have a really dense station network, while in other parts of the world, for example, in Asia, in Africa, in South America, Central South America, that you don't have much station network measurements. So that leads to a question that if you are using the station measurements to develop or evaluate your model, that are you sure this can really represent the model accuracy and performance globally, or it's maybe it's like biased or tilted towards certain geographic regions. And Amy will provide some much more interesting detailed examples in the later on of today's lecture. And so when you are using those in situ station-based measurements, you want to make sure, ask yourself several questions. For example, how representative, both spatially and temporally, are these data sets for your model development and evaluation? And are there any specific systematic bias or error in those data sets? For example, if you are familiar with the sea surface temperature measurements in those bucket methods, that people need to correct those biases in the old measurement methods, because when you take the bucket out of the water and then put them into the boat's deck and try to measure it, that there's a daytime bias and also there's those measurement bias in it. And what's the uncertainty of those data sets? And before you feed in the data into a model and use the data for the evaluation and assessment of your model. And the other major category of the observational data is the satellite-based measurements or observation. So because we have really wide range of the satellite missions that's flying in the sky, both from polar orbiting and geostationary satellite measurements, that satellite data has been really important in driven a lot of the AI machine learning applications in environmental sciences. But however, there are several things you need to consider when you are using the satellite data. If you're using only single sensor from data from single sensors on the satellite missions, that you want to make sure that you understand the quality of those single sensor data from satellite data. But when you are doing a lot of times analysis for climates and other type of applications, that you want to combine the data from multiple sensors and multiple satellite missions, so that you need to make sure those data quality are consistent and in your model development assessments. And also, last question is that is the satellite observation the same as that you want? So for point number 2, I want to point you to the right side of the screen, which demonstrating the satellite overpassing time and local times for polar orbiting satellite series from NOAA and from the EUMETSAT, which is European agency. So those are different satellites, polar orbiting satellites, from NOAA 7 in the 1980s to the most recent METOP A, METOP B, and NOAA 8, NOAA 18, NOAA 19 in the 2010s. You can see those satellite overpassing time has been slightly drifting to a earlier time, to a later time in the day. So based on those satellites orbital drift data. So when you are using those combination of satellite missions of those data measurements to categorizing some climate informations or climate change phenomena, you need to be careful to make sure those data has been carefully calibrated to make sure the quality of the data is suitable for your application. And the point number 3 about the satellites observation observing the same as what you want. One classic example is the land surface temperature. So in the satellite world, when we say land surface temperature, we mean the skin temperature, which is the how hot when you touch the skin of the surface, either it's like soil or the roads. But then a lot of times when we are talking about the surface temperature from the weather and climate modelings, surface temperature means the near surface air temperature, which is 2 meters above the surface of the measurements, so that there's a physical difference between those two measurements. So when you're using those two, if you want to use them as a proxy, you can do that, but you want to make sure that proxy is good enough for your applications. And so that's for the observation. And then we move on to the simulated and synthetic data. So sometimes you will use different terms, and I'm combining them here because they are similar in my mind, that they're based on a model or algorithms to generate those data sets that can be used for your model. And in this case, why people want to use simulated or synthetic data, because oftentimes the real data or the observational data can be incomplete or inaccessible. For example, in the satellite applications, oftentimes those near infrared and those satellite observations are in the visible band, which will be covered by the cloud. When you're interested in something that's under the cloud, the satellite data will not be able to provide any information for you. So you have to find other ways to do that. And so that's when some simulations and simulations of the data can be helpful to provide the information that you cannot get from observations. And sometimes also the real data cannot be directly used due to some restrictions such as privacy and other for some protected species, that even though you observe those data, maybe you don't want to use those data because the restriction how to use it. And so some common example in the environmental science applications, for example, the radiative transfer model simulation that has been often used to simulate satellite data. And so that can be used to do the retrieval of satellite products, and then further down the road to use for different applications. And then, well, if you put people who are doing real analysis, modeling, and then satellite data, people in the same room, they'll debate whether real analysis data is observation or not. But in my case, I'm from satellite and the observation world, so I definitely consider real analysis as a simulated or at least synthetic data. It's a combination of model simulations as well as observation together, trying to generate a spatially complete and long-term data set that can be used for applications. And climate model simulation is another classic example of simulated data that has been used for different applications to understanding the climate impacts in different future scenarios. And on the right side, just showing a simulated image from the ECM WF. Based on their model, they simulate a satellite image for the cloud and moisture in the atmosphere. But when you're using those simulated and synthetic data, that you also want to consider that simulated data also have quality issues you want to be careful about, because those simulated or synthetic data always have a model or algorithm in it to generate those data. So here is using the example of satellites again. So you can do radiative transfer model simulation to generate those simulated satellite data imageries, but then you need the input for this radiative transfer model to generate that. So oftentimes for my research, I use those atmospheric profiles of temperature and humidity at different levels of atmosphere, and to generate simulated satellite data to downstream applications. And sometimes those atmospheric profiles have quality issues. So you need to make sure that you understand the quality of the input for the simulation. And also the model simulation has its accuracy issues. On the right side, I would not say issues, have this quality associated with it. So you need to make sure you understand the quality of the model, accuracy of the model. On the right side, people have been doing the comparisons between the model simulated values for the satellite sensor errors, which is simulated in the red color, and then blue color is the real observations that you can see the difference in there, and it has dependencies on different the wavelengths of those channels. So you want to make sure you understand the quality and make sure this is suitable for your application. And now we can move on to the last category that we want to talk about today, which is crowdsourced data. Crowdsourced data can provide really unique opportunity to really fill in the data gaps in those traditional data collection methods. For example, on the right side, I show the data availability for the air quality from the Purple Air sensor network, which is a low-cost air quality sensor that has been used by a lot of people, especially recently, to monitoring the air quality for the areas where they live in. And you can see that on the Pacific West Coast that there's a lot of air quality sensors from Purple Air because of the Wi-Fi and other air quality concerns. And traditionally, when the EPA doing those air quality measurements, the sensor network setup is really expensive. And so that's why we have a limited data availability for those across the continental United States. But with the Purple Air, it can really help to provide much more information about air quality and fill in the data gaps where those traditional network that's more expensive cannot provide. And some other example on the crowdsourced data, including the CocoRES that is focusing on the precipitation for both rain, hail, and snow. And NASA has a program called the GLOBE. They measure, they allow people to provide the crowdsourced data from the mosquitoes to clouds and to different, and there's also one for aurora, those like really nice, beautiful measurements. And for NOAA, there's something called urban heat mapping program that has been doing those crowdsourced temperature and urban heat island mapping across different countries, different cities in the country, as well as now it's doing it internationally. But one thing I need to note is that there's also a challenge to establish those consistent data quality for crowdsourced data. So on the left side is a systematic review of the quality of the crowdsourced data in the in ecology research. So they compare those crowdsourced citizen science data sets with some like reference data sets that's being labeled by the experts, and so that considered as gold standard, and compare that with the with crowdsourced data. And as you can see, there are about at least a quarter of the data sets has less agreements, lower agreement, less than like 60% or 50% with those gold standards data sets that labeled by the experts. So that raised the issue that we need to be careful about the data quality from crowdsourced data. And on the right side is another example that from EPA. So they're comparing the Purple Air sensor network with those like federal, states, and tribal established network for the reference air quality. And they're comparing at different states, and where the red color is the raw Purple Air sensor measurements, and x-axis is the reference data. And so after the correction, the data points become blue. So that means that the raw data from the Purple Air network has larger bias and deviation from reference. But if you can apply some correction methods to correct that to a reference, so that data quality becomes much higher and can be really used for some of the analysis and research. So for feeding into your model development process. And so with that, I'm going to pass it on to Amy, who are going to share much more examples about how data relates to trust and ethical AI.
I think that we're both singing the same song. We just have some slightly different examples. So we have a paper that just came out this year that's linked down there below. From that paper, we have a table about all the ways in which AI can go wrong for environmental sciences. And I'm not going to talk about the bottom two ones, although Anne did talk about them. I think it was yesterday, but it could have been Monday because the days have run together for me a little bit. I want to focus on the first three, so that the issues that are related to the training data, because that's what today's focus is all the ways in which data relates to trust. And so the three things that I'm going to talk about are the fact that the data can be non-representative, including a lack of geodiversity. The training labels could be biased or faulty, some of which Douglas just talked about. And then the data can be affected by adversaries. Again, Douglas talked about crowdsourcing data without talking about adversaries. The fact is the AI needs to be created and used and trained in an ethical manner for all of the applications, right? And if we use poor training data we're just going to create a poor model. It is the garbage in, garbage out. And so we need, in addition to what he just talked about, I'm going to give you some examples. So let's go to the next slide. So starting with non-representative training data, one of the things that can happen in a lot of the phenomena that we're studying, and so I have two pictures here, a picture of a tornado and a really cool picture that I found of aircraft turbulence. I just happened to like it. Both of those are really rare phenomena, and you might not think that turbulence is rare if you ride in a plane and you don't happen to like the bumps in the plane, like I don't. But in fact, if you take the 3D volume of space, and that is to say the air above the entire world, turbulence is exceptionally rare. Tornadoes are very rare. Hail is rare, despite it destroying my roof multiple times in Oklahoma. These phenomena are interesting, and they're the ones we want to study, but they're super rare. And so if you don't pay attention to your data, you could have unknown biases in your data. You could have things that might cause your model to create the wrong kind of model. We'll talk a little bit about some specifics in hail in a few minutes. But in addition to all of that, data collection is challenging. In working on the hail project, which I've been doing for many, many years with a couple of different grad students that we've worked on this hail project, one of the things we talked about was, well, could we collect any data of hail forming? Well, as the answer to that is actually no, because nobody really wants to fly inside a storm, a drone, a plane, their car, anything to get destroyed, to have their sensors figure out exactly how the hail is forming, because their sensors also going to be destroyed. So data collection can be really challenging in some of these rare events, and yet they're really critical. Hail causes billions of dollars of damage a year. Another way to look at the non-representative training data, and I think that Douglas just covered some of this, but the sensors, in addition to having the biases that could happen, they could be non-uniform in where they're actually measuring. So in particular, those purple air sensors that we're talking about might be more prevalent in the affluent areas for the people who are willing to buy the purple air sensors, for example. This could also, if you're looking at a global scale, there might be more prevalent sensors in the countries that are more affluent as well. Along those same lines, remote mountain areas, oceans might not be well represented. So this is part of the non-uniform sensors. We don't have radar coverage in all of the mountains, as many of the people who study convective storms will tell you. The mountains get in the way. This isn't just we need to put a radar on top of a mountain. It doesn't work that way. The globe is round, and we need coverage that could see through the mountains, which really isn't ever going to happen. The oceans are not very well sensed, although there are people that are working on trying to improve that. The geostationary satellites are pretty much all we have right now. And along the lines of the satellites that Douglas was just talking about, one of the examples we have is looking at the start time of hurricanes. And as it turns out, more hurricanes are actually declared a hurricane in the morning, because that's when you can use the visible light spectrum rather than just looking at the other spectrums. And it turns out the humans that are declaring this are more comfortable with that visible light. So that could cause a bias in your data. If you're trying to train your AI model, it might suddenly think that hurricanes only become hurricanes overnight. Bit of a problem. I think that's it for this slide. Next slide. Along the lines of non-representative training data, climate change is both rare and unprecedented and very non-uniformly sensed. It's altering the underlying frequency of our phenomena that we're looking at. Things that used to happen 1 in 1,000 years are now happening 1 in 100 or 1 in 50. And if you have historical data that you're looking at and you're trying to learn to estimate your probabilities and be a reliable, trustworthy AI method, and you're testing on the past, you might not be correctly predicting things for the future. So many of these scenarios are underrepresented, and this could result in unintentional biases in our climate models. And more important, it could result in unintentional environmental justice. That is to say, you could take the data that you're coming in and you're giving the wrong probabilities and unreliable measurement, and you might unintentionally say, well, that's never going to happen. And now the people who are already known to be more affected by climate change, which tend to be the people of lower socioeconomic incomes, are going to get worse predictions. And now you are perpetuating environmental injustices. The picture I'm showing on the right here is from the floods last year in Europe. And with that headline of "The floods leave scientists stunned," they were unprecedented. Next slide. I believe that Anne showed this picture on day one, but I'm going to talk about it again because I want to do it from a slightly different viewpoint. This is another example of biased data. And in particular, what we're looking at here is geographic undersampling. This relates a little bit to what I was just talking about the mountains blocking the radar. You have geographic undersampling caused by your geography there. This is not caused by the geography. This is just, well, it partly is. The Southeast has the Appalachians, but largely what happened here is the NWS figured out where they needed to put down their network of radars, which are super expensive. So you're not going to put them in every single county, right? You want to cover as much as you can. They put down the network, and they're unintentionally missing the counties that are more populated by Black Americans. So that's what this graph is showing. It comes from Jack Sillen on Twitter. The link to it is right there. The high quality coverage of the radars is in the green there. The slightly, higher altitude, so not as good for the tornadoes coverage, is in yellow. And then you have a whole bunch of counties that are getting missed. And if you look at the underlying map where you have the gray shading showing the percentage of Black people that live in that county, you're missing the counties that have the higher percentage of Black people. And you might think, well, I hope you're not thinking anything like, well, this can get covered somehow, or, well, we can just create simulated data, because that's exactly what I want to talk about. Well, if we don't have the measurements, and if we create a machine learning algorithm that relies on super high quality radar data, we are now unintentionally not covering the tornadoes for the counties with the people who are more Black in that county, which means that we're creating a bias that we did not intend to do. By the way, while I put this graphic up, every time I put this graphic up, I try to point out that I don't in any regard think that the Weather Service did this on purpose. This just happens to be the way that they put out their coverage and what happened with their coverage. We can talk about how we need to fix it later, but for right now, you just need to be aware, if you're looking at your coverage of the radar network and you're training a machine learning model to do tornado prediction, that you have significant gaps and that your model might do something that you don't intend. Next slide. So humans create biases all the time. This is a picture of hail reports from 1955 to 2014 from a John Allen paper. And what's fascinating about this is if you put it on top of the road network, you might notice that it apparently only hails along roads. This is a little bit fascinating. I'm pretty sure that hail is actually more of a uniform sampling distribution across the storm, where the hail core is. Not that it in fact just hails where people live along the roads and in the cities. So this could be a problem. Again, you could train your machine learning model, and if it knew something about the underlying road network, it might learn that hail goes, for example, in straight lines along roads, or only hails along the roads, and it might be missing the farms and the underpopulated areas. Next slide. Just in case you think this is only true for hail, it is apparently very true for tornadoes as well. So there are more tornado reports where there's a higher population. There's a paper by Corey Potman et al. Talking about how you could potentially do correction for this, for the reporting bias, using a Bayesian framework. So if you're interested in that, look that up. But it is just the case that even though we have more chasers out there now, we still have a population bias to where the tornadoes are getting reported. Next slide. There are other ways in which the population biases could affect things. So we were talking about that we can't necessarily fly everything into a hailstorm to measure all the hailstorms. You rely on the labels for the humans. The humans are going to take their hail objects and they're going to create unintentional biases by trying to equate them to common objects. So rather than measuring the hailstone, they just pick it up, they put it in their hand, and they say, that looks like a softball, that looks like a baseball, that looks like a golf ball. And you get spikes. And you end up with a discrete distribution rather than a continuous distribution, when in fact, hail is really a continuous distribution. How might this affect your machine learning algorithm? Well, if you're trying to make predictions and you're trying to make a prediction of the distribution of the sizes, you really would prefer a continuous distribution that more represented reality and didn't have these ups and downs that are happening in here. Next slide. And just in case you think, okay, she's focused entirely too much on tornadoes and hail, I'm convinced tornadoes and hail have biases, but nothing else does. Well, let's keep going. Here's another example. This one is from wind data. The human estimated wind is shown in red, and then the wind that was actually measured using sensors is shown in blue. What do you notice between these two? The humans tend to round all of their wind measurements to 5-mile-an-hour bins. Nice little convenient bins, which makes it a much more discrete distribution than what actually is happening in reality with the blue. Again, if you're trying to train your machine learning algorithm to do the right thing, you probably don't want to rely on all those human labels. You probably want to rely on the blue labels. Also, you might be, wasn't quite ready for that. You might be unintentionally training your algorithm to do the wrong. you might be unintentionally penalizing your algorithm when you don't want to be doing that, right? Because if you're telling your algorithm that in fact the right thing is the red distribution here, but what's really happening is blue, and it tries to train itself towards blue, then you might be penalizing it for things that were actually correct, but it doesn't know it's correct. Next slide now. All right, hopefully this plays automatically. Yes, okay. So another bias, Douglas brought this one up. We both kind of did our slides separately without knowing that each other were going to do the temporal bias, but I thought I'd put it in there anyway because I think it's important to emphasize another one. The target phenomena that you might be trying to predict might be seasonal. And if you're training on all the data that's in the universe, you might miss the seasonal biases that your model should produce. So for example, the hail risk areas move around the United States by the season. And that's what this graphic is showing. It starts in the lower southeast. It moves up to the upper, thank you, Douglas, for continuing to play it. I should have put it on loop. Starts in the southeast, moves up towards Texas and Oklahoma. My roof can tell you about that. Moves up towards Colorado, goes up to the northern part of the plains, and then fades out. Next slide. If you don't handle that, you might be creating a model that isn't as trustworthy. And I've probably, for those of you who have seen me give a talk on this, have seen me give the full talk on this, I'm just going to give a quick reference to it here and with 2 slides. Amanda Burke, who's a PhD student of mine, is trained a model where she has temporal weighting on the model so that you could use multiple years of data, but you use all of May's storms, you use all of June's storms, you use all of July storms. So she's actually using all of the data that's out there, but she's weighting the storms for the month that you care about to be higher and more, to have the model care about the error on those storms more than the other months. And if you train those such that you train a May model and then a June model and a July model and an August model, you're going to get very different models. But you get a model that is accounting for what's actually happening in the month you care about. And I think that this same phenomena could also apply potentially to climate change. If we're training on 40 years of data that we happen to have, but we want to weight our more recent data more heavily so that we are weighting towards more of what's happening right now in the climate. Next slide. So what happened with that? We've been testing this for a number of years. The new version of this, that is the paper that's under review, was tested in 2020 in the hazardous weather test bed. And it was the first year that we had really fabulous results out of the model, where Adam Clark, who helps to run the hazardous weather test bed, said AI could be a game changer in his tweet. We really liked that. The result of this, of the multiple years of testing, is that we have improved trust in our model by the forecasters and a better model overall, because we paid attention to what they needed, which was they needed the probabilities to match what they expected, and we needed to pay attention to the seasonality. And by working hand in hand with those forecasters and by adjusting for the biases in the underlying data, we provided a better model. Next slide. I'm going to get us back to adversarial data too. So Douglas talked about crowdsourced data. I want to talk about how crowdsourced data can become adversarial data. So for the computer scientists in the audience, we often talk about adversarial data. And what often happens is it's shown with some little picture of a criminal, this little fake like clip art of a criminal, right? And you assume that that adversary comes in and corrupts your data in some way. And they've actually done real world data sets where they show, like, I don't know, pictures of a stop sign and somebody covers up pieces of the stop sign, pictures of the speed limit, you cover up bits of the speed limit. And those are real world adversaries that get out there and try to mess with the speed limit recognition. And people think, when I tried to start this, when we brought this up in our beginning of our discussions about our paper, people said, well, there's no adversary in weather. I beg to differ. So I'm going to give you several examples, one of which is even from last week. The one on the right here is a picture from a couple of years ago, 2020, where somebody hacked into the crowdsourced network called MPING, which is the Meteorological Phenomenon Identification Near the Ground. And it's a crowdsourced app you can download for free. I highly encourage it. It's a great app that you can report, freezing rain, hail, what size it is, etc. But somebody hacked into the network and decided to do stupid things. And the problem is that people are using this data to train their models. And people are using this data to make reports. The person who made this tweet, Elizabeth Lightman, is an SPC forecaster. And she said, as a meteorologist who relies on accurate and timely storm reports to aid in decision-making, this makes me angry. It's not cute or funny. The adversaries, I don't know what they were doing, but it was stupid and it affected everybody, right? So that's an example of it being deliberately hacked. Another one that happened relatively recently. So this just happened a couple of weeks ago, and then I have another one on the next slide, but don't change slides yet. Somebody was, and this went through the weather community, so if you were following it on Twitter, I'm sure you've seen it. Somebody was deliberately falsifying tornado reports. And as a repercussion of this, the local area put out a tornado emergency, actually, for what turned out to not actually have a tornado. And they did it because there was a tornado report that looked real enough from a supposed spotter that they thought there was a tornado and they wanted to protect the lives and property, which is what their job is. So these people who are crowdsourcing and hacking and saying the wrong thing and being adversaries are messing with the data. They could mess with the future AI models. They're messing with what's going on now. And there's a quote there. It has real life repercussions. In this case, it did not result in somebody getting hurt, which is great. But when you get too many of these false reports, it results in the degradation of our warnings. We have to make a warning decision in seconds, which, by the way, as an aside note, I want to point out that's really an important last sentence. When we're developing these AI models, when we talk about trust in our AI models, we want to make sure that they're able to use our AI models in seconds, right? They need to be able to trust it and not have to sit there and spend 5 minutes deciding whether or not the AI model is generating something false because it trained on data that was adversarial, for example. Next slide. This one just came out last week. So this is a very entertaining one. See, people, when I first started explaining this and saying that people would commit insurance fraud and mess with data, I think I got a lot of eye rolls. Like, nobody's going to do that. I beg to differ. So if you want to go look at that URL down there, turns out there was a person in Colorado who was messing with the mesonettes in Colorado by putting pie pans and taking pie pans to block the rain sensors and then using hot glue to block the rain sensors so that it looked like it was raining less. And he was doing this because there were payouts for insurance policies for being in a drought. And so he messed with the state climatological record at multiple weather stations in Colorado just to get insurance fraud for himself. Now, he's been ordered to pay this back, but there's nothing that can get the data back. Russ Schumacher has a quote in that article, if you go look at it, talking about now that they don't know how to trust the records, right? They have multiple years of records of rain data in the rural parts of Colorado where they don't know if they can trust them. And that's a real problem because especially as we're facing down more drought and we're trying to train our models to try to recognize this drought, now we have rain data we don't know if we can trust. And we can't go back in time and just make it up. Next slide. So I talked enough about how humans are adversaries. I think you've been well convinced that humans are adversaries. I want to make a point that I don't think Douglas made when he was talking about the crowdsourcing data. Weather is also an adversary. This isn't even crowdsourced data. This is just data that's being provided by sensor networks. Weather provides its very own adversary. It likes to come in and then knock out the power or take out the sensors. So on the upper right here, you have a picture of the mesonet, the Oklahoma mesonet. It recorded 151-mile-an-hour gust of wind. It was real, just in case you were thinking that, like, data quality issues, because an adversarial issue, you might look at that and say, that's a data quality issue, that's fake. No, in fact, it was not a data quality issue. However, it took out the station after that. So there were no more measurements, right? 151 miles an hour, gone till it got fixed. The lower left-hand corner is the power outages from a hurricane. So you're trying to measure things from the hurricane. You have all of these stations that are trying to measure the wind as it's coming in and it's landing. That's in New Orleans. It hit land, bang, you have no power. Now you have no sensors. Now you have no record of what happened, even in real time, if you need it in real time, but if you need it in post-hoc, so you can actually do your machine learning. So the weather provides its own adversary, and you really need to be able to deal with that. Next slide. Okay. We are going to do, because we realized from the past few days, you all have been giving us great feedback and asking great questions. We're going to do a breathing break. And also, since there's only 4 of us, we haven't been able to monitor Slido quite as easily as when there's 6 or 7 of us today. So we want to take a breathing break, go to Slido, and make sure we're answering your questions. So what example or topic has stood out to you most so far? And if you want to, the multimedia team wants to switch over to Slido, that would be awesome. And now we'll just hang out and see what happens.
Well, while we're waiting, Amy, I just want to also point out that COVID is also adversarial because during the COVID time, a lot of those crowdsourced data collection has been interrupted just because that there's less people going out and also there's less ship going out. So a lot of those like ship-based collection of the data are really limited during the past 2 or 3 years. That
is interesting. I had not thought of that. Thank you.
Yeah.
Looks like adversarial is getting lots of highlights. Yes, Chris.
So while people are filling this out, there are a few questions I'm going to highlight for Amy and Douglas so far. The first one, I think, is for Douglas, and I gave a nod that we're going to cover this tomorrow, but I don't know if there's anything you want to say on it now, is what is the best way to include uncertainty of these data sets in the models? So if you can talk about it now, or you can just say tune in tomorrow.
I would
It's
say
very
tune in
popular.
tomorrow. I would say tune
Okay.
in tomorrow, but there are a lot more like methods has been developed recently trying to account for the uncertainty when you're training your model. So, but that depends on you have an uncertainty quantification of the data itself first, because that is something you need to know the uncertainty of the data first, and then you can feed the uncertainty information into a model training process. That there are a lot of Bayesian-based methods and can account for that. And also people are adjusting the optimization and also the loss function, trying to account for the uncertainty themselves as well. So yeah, and there are a lot of community-driven methods trying to document and share the uncertainty methods about that as well.
Okay, great. I'm gonna mark that one as done. Other question, and I don't know if anyone's gonna be able to answer this, but does NCEP-NCAR reanalysis belong to observation or synthetic data?
Ooh, I throw that to Douglas.
I don't want to stir a debate or fight, but for me, personally, that would be considered as a synthetic data. But I know people think otherwise. That I think once you give us a beer, and then the fight can start just for that topic.
Okay, sounds good. I'm gonna, in the interest of following our code of conduct, just resolve that comment. Yeah, you bring it up again, we can. Okay. And we have another comment too, just please add bad choice of training data to the list of problems. I've now seen a couple of papers that do scientifically meaningless things with ML because the authors were lacking domain knowledge about the data they used and didn't understand its limitations.
Yes, 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 and yes, 1,000 times yes.
Awesome.
Are there any other questions? This is turning out very interesting. Apparently my adversaries were very exciting. They are. I find them very fascinating.
That's great.
I think,
Yeah.
I don't remember who's next on the slides.
It's me.
Okay. Do you want to switch over there?
Yep, I'm gonna switch over, but I think it's really can everyone see my slides?
No, it's just saying, there we go. You got it now.
Great. Awesome. Yeah, I think the Slido discussion is really really great. And now that we talked about the first hand, so you collecting the data oftentimes or use the data from some collections of data. So we want to make sure that you understand there are efforts ongoing on how we can understand the quality of the data and choose what data is most suitable for application, especially when dealing with the secondary data, which means that data collected by others and shared publicly or like directly with you that you can use. And you want to understand how the data has been collected and how the quality of it and how it can be used. So there are some community-driven efforts that I am involved in, which is called AI-ready data, especially started in the Earth and Environmental Sciences field, which is trying to provide those accessible and well-documented and reusable open environmental data for AI-driven AI applications. So data quality factors that is really important when we are talking about AI-ready data and how we can document the data quality and tools you can access the data. So some data quality factors that to consider when you're choosing those secondary data or using the secondary data, including the bias or the accuracy that I believe Amy and myself have shared some examples early on. So you really need to understand the bias and accuracy of that. And if you are data producers, then you want to make sure that you provide those bias and accuracy information about your data set so people can really trust the data that they can use for their model development. And then completeness and coverage that, again, both Amy and myself have provided different examples of how incomplete data can cause problems and on less trustworthy developments of the AI models. And then sometimes people are thinking about resolution and frequency. I think that depends on your application. So if you have an application that's really time sensitive, or you want to look at those minutes or hourly data phenomenon, then you should probably not use any monthly or like coarser resolution or frequency of data. Inconsistency that has been mentioned about the climate and other like long-term time span applications. So you want to make sure the data themselves is consistent throughout the time and also throughout different iterations of it. So sometimes that the data is put together from different networks. So you have network from US, you have network from Europe, you have network from Asia and Australia and other parts. So you want to make sure those the quality of those different networks of data are consistent with each other. And then the timeliness is another thing that I'm really glad that Amy mentioned about. Sometimes the trust depends on timeliness, because if you have a data that can only come in an hour later, so nobody is going to trust your application for that, just because the data has been really outdated when they need to be used in the model development process. So if you're interested in the AI readiness checklist that we provide, we just released this year, you can go to the DOI link that I put on the slides. And there are other ongoing efforts within the machine learning and computer science community to documenting and sharing the information about those data, make sure people understand what data they're getting into and how this can affect the downstream model development applications. For example, this one developed in 2018 called Datasheets for Datasets, that is by Temnet, Gabriel. So the purpose of this Datasheets for Datasets is trying to document and facilitate communications between the creators of dataset and the users of datasets. And Temnet was at Microsoft, I believe, at that time. Then she moved on to Google and then moved on to another institution, started her own institution focusing on some ethical issues of the AI applications in private industries. So within the datasheets for dataset, there are different sections. For the first one is the motivation. So why and who created this data sets, because sometimes who and why can determine whether this data set can be trusted to a certain degree. And then the composition of this data set, so what's in it, and you need to understand the content of data sets. And then going through the collection process, how this data set is created. So that becomes really important to determine, to contribute into the provenance of data set. For example, how you pre-process the collection of the data and then cleaning and labeling this data, that the provenance is important for users to understand the quality of it. And what's the intended use and what's the not suitable use. For example, if people the creators can specifically mention that this data set lack the quality for specific applications, then that will be a thing that the users of the data are aware of, so they are not misusing it. For example, if the people who lack the domain knowledge of this data sets, if the creator specifically mentioned that that should not be used for certain application, that can avoid some of those untrustworthy applications developments. And distribution, so it's who can use it and how this can be accessed. And the maintenance, I think that is a thing that has been gaining more and more attention. So how the data sets can be sustained and maintained, and make sure that that the data can be used in the future, can be updated when things have been changed and updated. So there's a long sentence quote on the right side. I still want to point out that data sets is aimed to increase transparency and accountability of those machine learning model development from the data's point of view. And that can also be used to mitigate those unwanted societal biases in the machine learning model, which Amy have already showed some really excellent examples in environmental sciences for that the bias in data can cause leads to the machine learning model biases. And that can also be used to select those more appropriate data sets. But this is really the beginning of this issue for data set that really requires much more community efforts to really make those data sheets for data sets much more common in a lot of different data sets. Another example I want to share is the data set nutrition project, which have similar ideas with the datasheets for dataset. It's trying to clearly communicate the intended use cases, data coverage, contents, and the potential harm and risk. This one specifically mentioned what's the potential harm and risk and of this data set if it's used in certain applications, and trying to facilitate proper and responsible machine learning developments. So it also focuses on the data pipeline. So when you selecting a data set, you want to really to integrate the quality of the data and trying to generating the labels for this data set to make sure that this you filter out those bad and inappropriate data set before you even start your model development process. And right side, just example, it's not environmental science, a specific example, but it's one of the a few examples they have as a nutrition label on their website. So it's a New York City's notice of property value data. So as you can see that it identifies different potential harm and risks in here caused by how the data is collected, that they contain certain socioeconomic biases and etc. So if you interested, you can go to read through their archive preprints about this newest generation of the data set nutrition labels. So that we are talking about the data, how you understand the quality and the data set themselves that can be used for your application developments. And now I want to bring us back into this the entire workflow. And as Chris had mentioned, that there are a lot of decisions as a developer you need to make throughout the workflows, from data to data processing, and then to how the model is, which model is selected and how the model is trained and developed. And here I want to focus on a specific workflow within the data part. So once you get the data and you will usually split the data into developmental set and testing set, trying to evaluate it. And within development, you also sometimes you will further split it into training and validation. So when you're having the training data set, you're using that to train a model, and you're using the validation data sets to optimize often those weights or hyperparameters. You will optimize your hyperparameters in the model themselves. Then you get your final predictive model based on your validation and or sometimes cross-validation of the final predictive model. And you're using this testing oftentimes because ideally it's an independent testing data set you can use to evaluate your final predictive model. So that's commonly we split the data when we are doing this development process. So during the training process, you'll never touch the testing data set to make sure that when you're doing the evaluation, that is it's independent. And to do that, there are like different ways you can split this data set there. Most commonly, people are doing just a random split, especially often it starts with in computer science that you just randomly split the data set and then feed them into it. And then people started talking about stratified split just because sometimes that you have disproportionately like lower portion of certain like labels or certain classes in your data set. You want to make sure those data can be selected into both your training and testing data sets. And then there's cross-validation, and there's leave one group out cross-validation. There's spatial cross-validation when we're talking about spatial data sets. So several things to consider when you are talking about this, how you split this data in your workflow. So what's the data structure? What's the structure of your data set? And especially in environmental science, do we have spatial autocorrelation or temporal autocorrelation of your data? If so, then you need to pay attention, make sure that when you're splitting this data into different parts, that you're not increasing risk of overfitting. We'll have some examples later on. And then what the AI model is used in this, and would then be sensitive of how the data is selected and what's the specific use case. For example, the real events or extreme events in weather, then sometimes that extreme events will relate to the imbalance, like sample or imbalance data set themselves. That can be an issue when we are not careful when we're splitting this data. So oftentimes on the left side, often people just do a random data splitting, especially generally that doing random splitting, basically just selecting those data set randomly into different parts for training, for validation, testing, without considering the spatial temporal conditions. And in geography or geoscience, there's something called first law of geography that's invented 50 years ago. So that's basically by Topler he states that everything's related to everything else. but near things are more related than distant things. So if we are closer in the space, then we likely to have higher or similarity with each other. So this is an example from the North Carolina State Climate Office showing the temperature this morning across the state of North Carolina. As you can see, when those stations are close to each other, they are much likely to have the similar temperature values for those. And so in this case, when we're thinking about if we're using those stations to train our model and evaluate our model, is random splitting the best way for an objective model assessment? If you, for example, in these two stations that's really close to each other, if you select one into the training and then select the other one into the testing, there's really strong correlation between those two. And it's hard to claim that the evaluation will be independent. So that can risk, when you are doing that for the model tunings, that can risk the overfitting that may lead to. This is another example of the landslide. So, and it's if you look at those observations for the landslides of those data points, when you're on the same side of a slope and very close to each other, you have much higher similarity in the probability to have experienced landslide. So that if you do not consider the spatial autocorrelation, trying to split data in a way that ignores that can lead to certain problems when you're doing develop your application process. So thus, in this geo computation with R, this online book, you can see that how you can do those spatial cross validation in different ways to make sure that you account for the spatial autocorrelation in your data. And so that's for the spatial autocorrelation. And so when we're looking at the temporal considerations, oftentimes we know that a lot of environmental science phenomena have those temporal autocorrelation. Looking at the time series of the temperature, that there's temporal relationship with them. So if it's hot today, okay, that might not be the best example, but and so within the time series that there is certain patterns, there's autocorrelations, especially when we're looking at climate change. When you're doing the trend analysis, people always ask you to account for this 1 month lag of those in this trend estimation to account for the autocorrelation of it. And so when you are splitting this data into different sets, oftentimes, sometimes people will suggest a chronological splitting. So you use certain time period for training, but you try to create certain gaps and for between your training data set and validation, because you don't want to have those spillover effects that the information from previous time periods spill over to next time period. So that's when you make sure that the data are relatively independent. If there's no absolute independent, oftentimes in these cases. And the last one I want to mention is the imbalanced samples. I mentioned about real and extreme events, that oftentimes the real imbalanced samples that for this two class example, you have positive and then negative. And for those real events, positive maybe really rarely happen. So that in the labels or in the data set you have, you have a really imbalanced portion between positive and negative. And if you are not paying attention to this imbalanced data sets, then you can lead to sometimes you call the accuracy paradox, which is that you have really limited number of positive cases, and then you have a really large number of negative cases. And if you do not address these issues when you train the model just say, oh, if I just give the results of negative all the time, I will get really high accuracy. And so I don't really need even to bother about the positive cases. So that can be a really big problem for those extreme real events. And so that is a big problem in some of those real diseases when people are trying to use those machine learning models to do that can cause big issues. So there are a variety of methods dealing with imbalanced samples from computer science and machine learning sides that a lot of them has been used in different applications. So here I listed a review paper and to see the challenges and some existing methodological development advancements on how to address those imbalance samples. And I lied. So this is my last 2 slides before we go to the next section, which is that, so the whole purpose of splitting the data in a correct way or in a more appropriate way is trying to avoid overfitting of your model. So ideally, so I borrowed these slides from Libby Barnes from CSU, which as they have an open tutorial slides with 200 some slides. If you want to learn more about the basics of machine learning, you can go to that DOI. That the slides is really comprehensive. So I borrowed this slides, which is talking about ideally when you train a model, you want to make sure the final predictive model can represent both training data set and testing data set really well. So that in this case is ideal case that the performance is both is similar or almost the same for both training and for the testing. But if you do not pay attention to how you split your data and the characteristics of a data set, sometimes you may cause a problem like this, so that it will try to overfit your model in a way to fit the training data set perfectly. While that sounds great for you when you have a powerful model, but when you're applying this model into other cases, for example, in this testing data set, you'll get really bad results just because that you overfit your model because the data set itself you try to fit the model too perfectly. So this is the purpose why you should pay attention to how you deal with your data during the splitting process. And I think with that, we will have another briefing break to see if any of you have any questions to address during this secondary data and workflows.
Yeah, so it looks like actually Slido has been impressively handled by, we've got David John jumping in there, we've got Marie, Monty, Amy, everyone seems to be getting great replies. I don't think there's anything outstanding that hasn't been replied to.
Okay, that's awesome.
So we're doing great on that. But again, it's a good reminder that you can use Slido and you'll get some of the top experts in your field to immediately respond to you. So it's a great opportunity to take advantage of because you got some great brains there hopping on, some good discussion. Now we pass it to Andrea.
Yep.
Okay, so we can continue now. We're going to move into a very specific set of principles that can help us create data sets that we do feel that we trust and are valid. And those concepts are reproducibility and replicability. So in 2013, there was a cover of The Economist that said, that was entitled, "What Science Gets Wrong." And what they were referring to in this article was the fact that some recent studies were finding that a lot of the research that had been published over the last several years was not able to be reproduced or replicated. And so this is a pretty big deal. And of course, to the public sounds extremely concerning, let alone the research community. So in response to this, the National Academies of Science, Engineering, and Medicine made a committee and did some extensive research on what's going on and how can we make that better. And there's a great report out that they put out in 2019. And I'm going to leverage heavily from that as I talk about reproducibility and replicability. So what do these terms mean? The R and R, not the R and R that some of us are thinking of. I'm going to start off by saying they're often used interchangeably. Depends on the field, it depends on the researcher, it depends on the time of day. Sometimes repeatability is thrown in there too. So just for the context of this, the purpose of this talk, I'm going to give you the definitions from this report and we'll stick with that for now. So reproducibility is obtaining consistent computational results using the same input data, computational steps, methods, code, and conditions of analysis. So this is essentially someone else taking all of your code and data and reproducing the computational environment and getting the exact same answers, hopefully. Replicability is obtaining consistent results across studies aimed at answering the same scientific questions. So in this case, we're going to have different researchers attacking the same problem, but they're likely using their own data. So reproducibility, once again, where we're taking the same data, same methods, same environment, and trying to get the same results. Why is it important? So for one, we reproduce our own results a lot of the time prior to publication. Sometimes we take a break from working on our research, and it's really nice to be able to come back and step back in and completely reproduce what we've already done. Also, other researchers that want to build on your work, the first step is often to reproduce your original results before you take that next step to building upon it. It does give us some validity and confidence in the results, although I'll touch on that in a second why that might not be exactly true. And it allows others to review all of your data, and that can really help you with the identification of errors and biases like we were just talking about. This is the way that it can happen. So when we assess reproducibility, so are we able to reproduce the study? There are some steps that are generally good practice. First is choosing a metric or attribute of interest to compare. So if we're comparing data sets, that are creating several different outputs, we really want to focus on the outputs of interest. We may not care so much about certain fringe elements, but we do need to make sure we choose these attributes carefully. And then we have to thoughtfully characterize the uncertainties. In the computational age, this is actually it's important, but these uncertainties in reproducing results are going to be very small. They're going to be limited to maybe bitwise levels between computing systems at most. So computational reproducibility usually leads to near identical results. I'll show some exceptions on the next slide. So it's important to note that success in reproducing results does not guarantee correctness of the results. If there's an error in the code or a bias inherent in the data set or the software, that is going to be reproduced by the reproduction study. So there are a couple of different types of reproducibility studies. The first is direct, which is honestly pretty rare, which is replaying the computations to obtain consistent results. So this is where you literally take everything and just reproduce the results and you're done. Indirect reproducibility studies do assessments of transparency of the data and methods of studies to try to understand if it's possible to reproduce the study. These are much more common, obviously, because there's really not a lot of funding to just redo people's results. Systematic efforts to computationally reproduce results across various studies have found that they've failed to do so. Like I had mentioned with the replicability crisis, less than half of the time have they been able to do so. And that's been evaluated as due to insufficient details. So some sources of non-reproducibility are non-public data and code. So sometimes we're using proprietary code, proprietary data, or social data with large restrictions on how it can be accessed and shared. And so those cases are just not going to be reproducible outside of the individual research group. Inadequate record keeping and non-transparent reporting, that's really I put asterisks there because those are the aspects of the replicability crisis. I'm sorry, I'm going to trip over those words several times. That were brought up, and that's a key issue that hopefully will give you some tools to not do that. Obsolescence of digital artifacts, lack of continued curation. We all know this happens. When a project ends, we try to curate the data sets and the code and the files, but more new projects come along and it gets really, really hard to keep up with the older artifacts. And so that's an issue when it comes to reproducibility, and we need to find ways to address that. Flawed attempts, so this probably doesn't happen quite as often, but sometimes maybe researchers who are trying to reproduce results just don't understand the methods that you used or misunderstand what's happening. So there might be some issues with their reproduction techniques, and barriers in the culture of research. I sort of hinted at this. So there's just a lack of resources and incentives for reproducing. Novel research is what gets published, gets funded, And so this confirmatory type of research happens a lot of the time sort of quickly behind the scenes and doesn't even necessarily get published. It's more of like a gut check. So we don't know what's happening. So moving on to replicability. So this is where scientists are working to answer the same scientific question, but they're each using their own individually obtained data. So why is replicability important? It's one of the key ways scientists build confidence in the scientific merit of results. I mean, this is the way that we build consensus, basically. And it really does help us. Help us try to identify biases and outliers. And it really is, this is honestly the key to scientific investigation and discovery is we don't have a lot of results that we feel are robust that really have just come from one study. We often do many different studies in order to really query these scientific issues. So thoughtful identification of sources of uncertainty is really, really important with replicability. I'm going to spend a little more time with that. And of course, all of this has some pretty major implications for trust and trustworthiness. Do we trust the scientific consensus? Will it based on the results of the replicability? So in assessing success of replication, it can be done in a number of ways. So once again, choosing our metric or attribute of interest is really crucial. It's even more crucial now because the different studies will have likely different methods. They might have different goals. And so you really have to figure out what you're comparing from study A to study B that we can expect to be the same or similar. And it has to be something that actually interests us. Thoughtfully characterize uncertainties once again, and exact replication is really not possible. We're using different data sets. So we need to define consistent results some other way. And one good way to do that, at least from the Academy's report, was using a proximity uncertainty framework. Once again, success does not guarantee correctness of results. Just because two studies confirm something does not mean that that thing is true. There's a lot that goes into building scientific consensus. Systematic efforts to replicate results. Once again, the replication crisis have found that less than half of the time the replication is possible. And a lot of that is blamed, once again, on insufficient details provided by the original study researchers. But it's more nuanced. There's a more nuanced interpretation to this lack of replicability than with reproducibility. Because even when a study was rigorously conducted according to best practices, correctly analyzed, transparently reported, it may still fail to be replicated. That is actually how we find new results. And that's how we find groundbreaking or novel, interesting things. So there's actually a lot of good to be had in the lack of replicability from the point of view of science. And a single inability to replicate does not mean the original results are not correct. So I just wanted to touch just really briefly on uncertainty and replicability. Uncertainty is just a key element of replicability, and it's something that has to be really thoughtfully considered when doing a replication study. So we can look here at, these are all different studies that are trying to get at a particular scientific constant. And here are the estimates of the constant, and then there are error bars. And so when we compare studies A and B, we can see that even though the constant values are pretty different, the error bars are quite large for those studies. And so we have a lot of uncertainty assessed for each of those studies. So the estimate from A is within the error bars of B and vice versa. So we might consider this a successful replication. Now, if we look down at C and D, we can see that we have really, really, really close estimates for that constant, but the error bars are really, really small. So it's really hard to see in this figure. We may consider this replication, successful replication. We may not, just because the precision of these estimates is so high. And then when we look at A versus C, we can see we have the study with a lot of uncertainty and then C with a very, very little uncertainty. And this should give us pause because we want to consider, like I said, both proximity and uncertainty. And it just is not clear that the results from A and C are actually consistent because there's so much uncertainty with A, whereas we're very sure about C. So that's something where we really do have to work hard. And I think the session tomorrow is going to focus more on uncertainty estimation and how we do this. So as I mentioned, non-replicability could actually be a good thing. So I've taken the report has taken replicability reasons for non-replicability reasons and split them into helpful and unhelpful. So for helpful, we can consider not being able to replicate somebody's study as, well, maybe it's a discovery of an action or interrelation or a source of uncertainty that we didn't know about. Those are all actually good things. We have new things to explore, and there are parts of the picture that we just don't understand yet, and that's actually pretty exciting from a science point of view. The nature of the problem under study and the prior likelihoods of possible results also affect replicability. Areas that are more complex, groundbreaking, cutting edge, novel, all those buzzwords, but instances like that or studies like that are generally less replicable than studies of processes that we have a pretty good handle on. So we might be just working in a really exciting, novel, cutting edge field. Unhelpful reasons are, there's a lot, including human error and bias, which are always potentially there, and we should always be keeping a really good eye out for. And misconduct, unfortunately, sometimes happens. Publication bias, once again, publications tend to not necessarily want to publish replication studies, so that sort of influences how they are done and how often. Inappropriate statistical inference, that's an important one. Statistical significance is not always the end-all be-all of deciding that your results are good. We shouldn't necessarily just throw out all the results that aren't statistically significant because they're part of the overall picture and we can get led astray. So basically, the bottom line here is that non-replication is a normal consequence of studying complex systems. In a field, if we have too much replication, too many replication studies, we might be just doing conservative research. We might be missing important discoveries. So that's sort of an indicator that maybe the field needs to sort of push the envelope a little bit more. But if we have not enough replication, then we have to be concerned that some of our results, we may not be as confident as we would like to be. There may not be as much consensus building in that field. And so we need to find a balance between replication, which is hard because once again, we're not getting a lot of funding to replicate results necessarily, and not having enough and just sort of studying new things all the time and never building consensus on anything. So the steps necessary for reproducibility and replicability involve, first of all, the input data used in the study. We really, really need to be sure that we are documenting and collecting the data. And in the current environment where we're using really large data sets, sometimes that's just not possible. And so any binaries or scripts we've used to process the data, that serves pretty well also as a substitute for actually supplying the data sets in some situations where maybe supplying the data sets accessibly and readily would be more appropriate. We need detailed descriptions of study methods. A lot of time that serves as code and scripts as well, and information about the computational environment. That's really important given almost everything we're doing is using high-level computing, and we need things like dependencies and libraries to all match up. So capturing your environment under which you did your study is extremely important. So before I go back into a little bit more, a little follow-up on how to facilitate R&R. Let's have a quick little break. And I guess in your own words, why should we care about reproducibility and replicability? Love to see the Slido results here. So I will get out. Ugh. Right, authenticity, integrity. And if you can't, yeah, they are probably not valid or trustworthy results. So trustworthiness comes into play quite a bit. Finalize and reach consensus. And trust, yeah. Right, it's just such a, in some ways it seems like such a simple thing, but you know, as someone who's developed code for many, many years, this is really, it's really nice to see this turn to attention to these topics. Yeah, honesty, right. There's no better way to prove that you've done things right than to lay all your cards on the table. And it's especially important with AI, right? Profit motives to deceive, right? I hate talking about that, but I know there's a lot of pressure out there, and that it certainly opens it up for the potential. So, well, this is great. Thank you so much for responding. And I'm going to go ahead and move ahead to just some quick notes on how to user error. There it is. Okay. So now I just want to briefly touch on how to ensure reproducibility and replicability. So Doug has already talked about provenance or mentioned provenance earlier, and now I'm just going to step through it a little bit more in detail here to, you know, because I don't know if you're like me, but probably not, because I'm probably a lot older than a lot of you, but this was not something that we did very often in my early days of software development and coding. We did a lot of just writing version numbers and writing a lot of notes on top of our code and scripts. And it's made it very difficult to share that data with other science and researchers. It takes a lot of effort to do that. And I'm currently honestly doing that myself, trying to share some code with fellow researchers and realizing I wish I'd done a better job of provenance earlier on. So this is especially crucial with more complicated systems like AI and machine learning algorithms. So, and especially important when we're talking about data sets with all of the potential issues that Amy and Doug have been talking about in the previous hour. So when we think about provenance, as I mentioned previously from the report, we focus on these key areas. So we have data, which includes the database, input files, and parameters. This might also include intermediate data sets that are created, a lot of info about cleaning. What did you do to QC the data? We also need to know a lot about the computational environment. We use so many different software packages and platforms that we really need to make sure that this environment is replicable. And computational steps. So this is our methods. What did we do with the data? And nowadays that includes a lot of scripts, potentially interactive notebooks, and just basic scientific workflow being documented and easily accessible. And then of course, we have our published results. And this is where our reproducible experiment should come from. So to reiterate, with data, we can use things like version control That can include Git and other platforms. Our document cleaning and QC practices. We need to document cleaning and QC practices, and that needs to be readily available with the data. That may involve providing scripts and code that did these things, and providing original data sets and intermediate data sets. As far as code and software goes, once again, version control. It's a really useful tool, and it's going to continue to be so, especially as our code and software gets more complicated. Computational environments, there are some tools out there, including virtual machines, but you need to make sure your VMs include source code and documentation, no black box virtual machines. Well, you could also use containers, such as and computational notebooks such as Jupyter notebooks to encapsulate the entire environment. So these are just some handy tools, but the bottom line here is that we need to document everything in order to facilitate replicability and reproducibility. So there is an example framework from Mitchell et al. 2019 called model cards. And there's currently no standardized provenance for machine learning and AI models. So this is sort of a first step towards, here's a nice simple idea that maybe we can all use. And the idea was to encourage transparent model reporting. So here's an example of a model card from a study that was looking at toxicity in text. So they were reading through text and coding for toxic statements. We can see some of the key elements here. We have benchmarked evaluations in a variety of conditions, context in which models are intended to be used, details of the performance and evaluation procedures, and then we'll add other relevant information. So we can see really, these are really short. So this is not necessarily everything you would need for good provenance, but we do have model details, a few bullets, intended use, factors, metrics, and then ethical considerations, and training data, evaluation data, and any caveats or recommendations. Pretty short, and then a couple of plots of some of the brief quantitative analysis. And the idea here is that it can be used to document any trained machine learning model. And like I said, it's not comprehensive, but if we all had this for every model we developed, just ready to share, this would be a great first step towards democratizing machine learning and AI technology. So I think it's a pretty cool idea, pretty modest, but yet pretty doable given how much effort can go into provenance. So I'll turn it over to Chris.
All right, thank you, Andrea, for that really great overview of all these important things. And I think it's gonna answer a lot of questions in the chat too. I'm trying to synthesize it and pull it all together really quickly here because we're about on our break. But we see that a lot of the decisions that we make throughout this process, not just the user model output arena, but all the way back through to where the data is collected and what we're kind of assigning as the key points for our data through to the development, data processing, and all those different points. But we also want to ask if there are essentially points that we shouldn't be open on. So is all science should be open, and shared, and we want to make sure it's reproducible. Because there's also concerns about privacy and protection of rights, preserving trust. And so I think, a couple of good examples of what this, when we think about this, is there are some data like from interviews that shouldn't be shared. They're a researcher and a respondent talking about, very, personal or very, sensitive details, about the loss of life that they've experienced in their families related to severe weather, or things that could be potentially exploited by others. Or it could hurt their, standing in their community, these types of things. And so thinking that we don't always, the answer isn't always to publish and to share everything, because sometimes those are really important stories or really important data that we should as researchers keep and not share for everyone. And so thinking about maintaining privacy and maintaining trust in that research entity is really key, and knowing that not all data is going to be shared in some ways. And this also gets into an idea with on the AI side, not just on the social science side, is about the idea of differential privacy you talk about. So theoretically, you shouldn't be able to learn too much from someone from an AI algorithm because their data is included in it. If you remove them, it shouldn't hurt performance too much. And so thinking about if we can maintain those types of protections of rights and preserving trust is going to be really, really key. And we've talked a lot about some of those things in different ways, kind of what are the adversaries and what are the problems that can go wrong, and just thinking, are we really doing the best to, serve underrepresented communities and not exploit them in a lot of ways. And so if you hit the next slide, we're also thinking about, there's a lot of these social questions, and that's what I think TAI4ES does really, really well, is we're taking this interdisciplinary approach where we have the risk-com and the social science part, focus in on this whole process too. So the next section, we're going to talk about understanding these points and the user interactions and how we're studying those things and digging in and how we can communicate a lot of these different issues. But I know we're just 5 minutes over, so I'm going to stop here. And we'll take the questions in Slido. We're going to skip the next one. We have the full break here. And so it's down to 10 minutes. I think we could probably still get 15 if we want. What do you think, Amy?
I'm okay with whatever you want to do.
Yeah, let's just still do 15 minutes. So we'll come back in 15 at, let's do 10:50 Mountain Time. So you have 15 minutes to take a break, relax. We'll hit on the questions in Slido in the meantime and see if there's anything else there. And as well as eat our lunches and all that great stuff. And we'll see you back in 15.
Okay, welcome back. I am going to attempt to share my screen. And hopefully not do anything crazy with my screen sharing today like I did yesterday. Okay. Can everybody see that right? Let me know if not, because I can't see the chat anymore. So
Looks good.
Welcome back. Thank you. Welcome back. What we're going to do for the second half of today is talk about how we can use case studies, which is a big part of data, since today's theme is about data. Well, the theme is really data and case studies, but how we can use case studies to improve trust. So I'm going to start with an opening question to make sure everybody's back and warmed up. And the question is, this graphic is from a paper from Randy Chase, who presented yesterday, my postdoc. He's working on a second tutorial for machine learning. We have a first tutorial that's already available in early online. And so just so you know where this graphic is coming from. I'm not going to explain it much more than that. It's just a graphic showing, some objective verifications, 2 ways to objectively verify a whole bunch of different machine learning models. And the question for Slido is, why can't we just verify all of this objectively? Why do we need to look at case studies? And is using multiple metrics to explain model performance enough to build users' trust? And I am going to hopefully stop sharing and hop over to the Slido. Funding bias, I love it. Already an answer. I would love if the funding bias person wants to put a little bit more about that in there. Because the funding agency wants the case studies, or because they think the funding bias might be messing with how you're evaluating. Contextual clues, I agree. Yes, opinions are different. Paradox, we could not verify the model with the real unseen data. So you're answering the question why we need some case studies. Yes. Hard for end users to understand. Definitely. So when I was saying that why can't we do it all objectively, there are a couple of you who are saying things like there's no true data. We do have the data, right? We have all of the data. The question is, why do we need to go study these case studies? Why can't we just look at everything objectively? Edge cases, definitely interesting and perform unexpectedly. You don't know everything about the thing you're studying. Also a good point. You might do well on the majority events, but not on the outliers. Related to that, I would say, by the way, you might do well on average, but not on the outliers. You want situations that exemplify certain biases. Oh, this is scrolling by so quickly. There is no real objectivity. That will go with, I would say, there may not be one specific metric that will answer everything you want. Metrics may not be completely understood by end users. That's a good one. Case studies are a trial of use cases. Yes. A few more people typing. Reviewers will be unhappy because it contradicts their findings. Oh, that's a hard one. That kind of gets into the funding bias. Every user has a use case and end goal, and users are visual and not metrics. These are all great. And you understand the consistency of the data in and out. I love it. All right, it says no more people are typing, so I'm going to hop back. I think I can just reshare. Hold on. So I'm glad to see a lot of the things that were coming through are very much what we've been talking about. So these are some from some interviews. There were interviews that were introduced on day 1 and day 2 of summer school. These are different quotes. They weren't used on day 1 and day 2, but they highlight what our forecasters have already said about the need for case studies, and certainly go with what you were just saying in the results in the poll. Getting to use it more and seeing how it does in different kinds of convective situations. I can't think of a better way to raise the trustworthiness. If it's not perfect, that's okay. Knowing how it performs in certain situations and seeing that really, really increases the trustworthiness. So I like there are 2 things out of that. One, they know it's not perfect and they're acknowledging that and they're saying that's okay, but they just really want to see how it works in different case studies. And then another one, we tend not to be classic supercell land. Storm mode is very messy. So what we work in an area of Oklahoma or Texas, discrete, very pretty supercells, we tend not to get. So I would say I need some time to make sure the guidance is encompassing the sort of weather we see here, where here is redacted. We know it's not Oklahoma or Kansas. Another argument for case studies. So a reason in that case for case studies is that the model and the objective verification might fit in with what somebody answered about it's working well in certain cases or majority cases. If the majority of the supercells are in Oklahoma, Texas, and Kansas, which is probably the case, then they want to make sure it's still working in their part of the country, wherever their part of the country is. We've seen a general need for case studies across multiple studies. So the previous set of slides were on results from the interviews that we've talked about. This set of results is from David Harrison's PhD thesis, which he's about to defend in 2 weeks, 3 weeks, something like that. So the citation for his thesis, it will be online at the end of July. He also had an AMS talk that talked about some of these results. And there's going to be a paper as well, but I just wanted to highlight, well, a little bit out of this. So in 2021, he participated as part of the virtual hazardous weather testbed. It's been virtual 2020, 2021, and 2022. And they had 133 different participants from a whole variety of institutions that are listed there. And he asked them a whole lot of questions about what was important to them about evaluating probabilistic products versus evaluating machine learning products. And the answers that I wanted to highlight here are the 2 that are shown in red, which is that relate to the case study. So something that came up in the results when I asked you the question as well, is that you want to know what it might fail. You want to know the limitations and the possible failure conditions. And that case studies are one way that you're going to be able to get that. You need to know the edge cases. You can't just see the objective verification, but the objective verification is essentially giving you the average performance. And then these are ordered by the order in which they were most important. And so the 4th one down says very specifically the performance of the product in case studies itself. So everybody who was taking the survey was agreeing that that was really, really important. Of interest, some of the other things that one might think that are less important that you might have thought they were important, down to the bottom, for example, previous experience with the developers of the product. They don't care how good you are at making these products. They care how good this product is, and they want to look at the case study. I think those are all very interesting results, and they point to the need for case studies. Next slide. Oh, wait, I'm doing slides. Haha. So case studies are important across all aspects of guidance. They are not just important for AI. And so that's something else that I just wanted to emphasize. These results come from a different study from Julie Demuth, who's part of AI4ES, but this is a publication from outside of AI4ES. Where the 2 forecaster quotes, the thing for me, especially with anything new, is have they tested it out west? Does it work out here? Right? They don't care if it's an NWP model or anything. They want case studies wanting to know if it's going to work in their area. How well does it work out here when you have a sparsity of observation data? You have to gain confidence it's going to be useful for me here. And that particular forecaster is looking at rain. And the next one, I also want to see, if you look at the model verification over the whole winter season, this particular model may do the best, but is it doing best when it really matters? And they're looking at very specific edge cases. And I think that is something that we need to talk about when we're talking about how to pick case studies, which is something we're going to talk about in this section. We need to pay attention to what the forecaster needs are for those case studies, what it is that they are looking for. Maybe a model does best at snowfall amounts over the whole season, but is it catching the higher amounts, or does it under forecast, for example? Again, coming back to does it do well on average, or does it do well overall, and does it do well on a specific case study? So I know we just started. We're giving ourselves breathing breaks to make sure that we are not missing anything in Slido. And since I can't see Slido, I'm going to ask Chris if there's anything in Slido we need to tackle.
Not yet. Otherwise, it looks pretty good. Nothing's coming in too hot.
Since we're running 30 seconds ahead of the live stream, should we give it 30 seconds to see if anything comes in?
We should do that. Good idea. We're in the future for them.
So just let me know, because in full screen mode, I can't see a darn thing.
Sounds good. Looks like we're good. Nothing's
Okay.
coming in.
Excellent.
All right, then.
I think I'm switching over to you now, right?
We are, yes. So
Okay.
you did a great job setting up the user perceptions here. So importance of case study, knowing about performance and a lot of these different ideas. And we've hinted at a lot of these points throughout the last couple of days too. So what do people need? What is important information? You talk about that and think about that in the Trustathon as well. And so what we're going to do in the next section is dig in a little bit about how we're communicating this type of information to users and how we're, with the Institute here, AI4ES, digging into these questions and these problems. What information do people need? How do people react to these different types of things that we're talking about here on the developer side, on the end user side instead? So if you hit the next slide, this fits into our risk communication goal. And we showed this, or actually Andrea showed this on Monday, talking about interdisciplinary work, and was just using it as a way to highlight that we're all working together to get this trustworthy and use-driven AI ML products. But part of this is going through and looking at research into how different end users, so those ones kind of listed on the right, National Weather Service, USGS, and across like DOT and all sorts of different kind of examples in case studies, are really interacting and responding to the specific detailed development information about AI. And so we're working on those semi-structured interviews right now with different users. And we've talked a lot about the ones in the severe weather space. What we want to do here is introduce a new product, one that we're currently working on. It hasn't gone in the field yet, related to coastal fog. So if you hit the next slide, this is an effort led in AI4ES by Philippe Tissot and all the great collaborators from Texas A&M Corpus Christi. And so it's called FogNet, and it's used for doing fog predictions on the coastal environments. And it's right now focused on Corpus Christi, but it's a 3D CNN that's physics-based and has about 30 different inputs based on NWPs and satellite imagery. You can see there's a complex diagram for it. And I can't do it full justice in exactly the mechanics of how it works, but what we have here is, and they're in the slides listed and linked here, the papers about it. So they have several papers that have walked through the details and mechanics of this model in different versions of it, both in 2021 and 2022. And I'll let you, if you all are interested and you can dig into it more, that's great. And you want more follow-up questions, happy to answer those in the chat. We can ping Philippe and Hamid and Evan. I think Evan was responding yesterday to a couple of different XAI things. But can move on to the next one. We're thinking about how we're doing interviews with this. So we're taking that product, the coastal fog prediction system, and doing interviews with forecasters to understand, what the needs are and how we can better tailor this product and communicate about it to make it more effective in their decision context, which would be using it for forecasting coastal fog in their area. And so what we're doing is, in this interview process, we have the questions that we've talked about in the earlier days. So what does trustworthiness mean to you in the context of AI or ML, interpretability, explainability? But in the second part of the interview, which we haven't talked about yet, it's interactive, where we have forecasters sit down with guidance. And it would start off with a slide like this. It wouldn't have a Slido link on it, but just some basic information and some output. Be like, okay, we ask you, what do you need to know about this guidance before using it? We tell them it's a 3D CNN. We tell them exactly what it's trying to predict, and we give some examples of the output. And we ask that open question, which I'm going to throw to you first. What else would you want to know about this model before using it? So imagine that you're a forecaster and you've given this. What do you need to know before you're going to apply this information to your job? So I'll throw that open in Slido. Hopefully that pops in. All right, great. And so you'll get that same question. What would you want to know about this model before being able to use it? So to push the, and so actually it looks like we'll have to do this slide if we want to activate the poll. It's not quite active yet for me. There we go. And so actually for this one, it might be helpful if you have the slides at home, but just knowing that this is the output, right? So thinking about what would you want to know about a model before being able to use it. It's a little tricky because you can't see it. So what does it use for input? Yeah, so the exact inputs are. What else would you want to know about this model that predicts fog before using it? Verification method. So how is it verified? Clarity of the end user's goal. Yep, so how are you going to use this for your job for sure? Sensitivity, attributability of the model, features, robustness, structure, resolution, where it fails, who else is using it? Great, these are all good points. Is the model physics-based? Excellent. Skill metric, subset verified visibility. Okay, awesome. What parameters does it use to create the predictions? Inputs, excellent. Failure modes, for sure. So we want to know, when is it not going to work? When should I be a little more skeptical of it, or should I not trust it? How reliable / consistent is the model? What was the training data? False positive, positives, negatives, etc. How much data it contains? The workflow, like how do you use it and how is it made? Input data resolution, limitations, how it works, resolution and model biases, how much data was trained on. These are all great. Awesome. Do I have anything ready to use the model? Okay. Awesome. The architecture, how much training data there was, could be made operational. Yeah, so is it kind of given a blessing by your organization? Biases, vulnerability to disruption and its accuracy, skill scores. Okay, this is great. So actually we'll flip back to, was it ethical in my context? Yes, that's awesome. We'll hold on to that one too. This is great. And so we flip back to the
You want me to share the next slide, since the next slide also becomes a poll?
Yes.
I can. Okay.
Yeah, we'll sit there and I'll introduce the poll for a second.
Okay.
So what you're seeing there's a lot of information when we initially present, someone with a model that they're thinking of. And a lot of these same questions are what people also list, the forecasters say. And so what we've done is we've thought about what information to include, and I'll show you some of that later. But then I'm going to put you, instead from your user hat that you just had on. So you're a developer and you know that the users have these type of questions like you just asked. And you know that case studies are important, like Amy's outlined. How do you pick them? So how do you answer your own question I just posed to you? What is the best way to do this? And so we'll flip to Slido for a question of 3.8. Yeah. So there's some options for you. You can select multiple of them. What do you do? How do you pick these case studies to answer your own questions and your own concerns about the model? Throwing it back to you. Ooh, they're changing live here. You can't quite see them on your version, but we've got select examples, the most common cases, okay? The worst hits, select examples of rare events. The best hits is a little less popular. Ooh, worst misses. So when it did poorly is coming up to be hitting that failure mode point. So those people who said failure mode was important to know are probably the same people saying, knowing the worst misses. Yeah, selecting the most common comes up again here. Good variation. This is interesting. Can we get a scroll? I don't know. Are there ones I can't see? I'm pretty sure there are a few more. Who's not popular? I'm gonna check those out. Actually, I can see it on my end too. So select events from a certain time. So of day or of year is not as popular, only 38% of people selecting that. Examples of rare events is now down to 33. Random cases is to only 25% of people. Geography is only 36. All right, so this is good. We keep these in mind. So we're gonna show you what we did or what we're doing in this setup. And we can flip back to the slides because you're hitting on a lot of the same ideas that we were. And so the first thing we're showing actually in this slide deck, and I'm also going to put a disclaimer that not all of the things I'm showing are perfectly case studies or not. Andrea pointed that out when we were practicing yesterday. It's like, oh, some of this is kind of a case study, some of this is more verification. And so we're just covering this a little bit more broadly right now. But the first thing that we're showing is actually something that a National Weather Service forecaster did with this model, where they looked over the total number of cases where there was fog or no fog, and then looked at the fog type for each of those. And they found that advection fog was much more common, as opposed to radiation fog. And so it has the majority minority bias here for training the model. So it does really well for advection fog, but it doesn't do super well for radiation because it hasn't seen very many examples of those, which on the developer side, you can see makes sense. And so that's something that we're communicating. This is information that we'll give to the forecasters as is to explore and see kind of how this impacts their trustworthiness, their view of how trustworthy AI is, being upfront and transparent. So we've heard transparency a lot so far, and that's what we're trying to test. How does being upfront about failure mode actually impact how people view a model that they could potentially use? Then also being very clear about where the failure modes are is what we're going to start to empirically evaluate here as well. So it hits on a lot of those things that you were saying. You could think about how we could use this to present a more specific case study, about those different types. Like, here's where the common events are, here's what you're likely to see, and how do we communicate when it doesn't do well. So hit the next slide. We also have, people mentioned verification, like we want to know how it does. We're providing a lot of verification metrics, which I'm not going to walk through right now, but this is also what we're showing to forecasters as well, to get a sense of how important are these stats, but also giving them a breakdown of what they mean. So here's a sentence or two about what each of these verification metrics are, and here's how they do for the model. So the different lead times that we're presenting, because we want to get a sense of that this is important information. But we also, if you hit the next slide, we're not just stopping at the common types of verification, we're getting a few different ones. So we talked about CSI, I actually think on Monday. A few people asked a question, and in the question to Slido, I just stole this interpretation of CSI because someone asked what it was. So if you're wondering if you've seen this text before, some of you may have. But we're digging into more of these skill-based metrics and also metrics that are designed for rare events and see if these are important things that we want to communicate, or if the end user just doesn't really care about them. And so we're getting a sense of that and trying to evaluate that so we can come up with better recommendations and understand how to communicate our models a little bit better. And if you hit the last one, we're also getting some sort of relative performance. So we're testing out how, when you take a new product, you compare it to something you already have. So FOGNA is the model that we're shopping out here, and then we're showing a direct comparison to the href, which is guidance that someone in the same kind of user space likely knows and is familiar with. So like, how does it impact my view of the model if I can see how it performs compared to something I know? And so we're showing a lot of these different ways to start to understand how we can communicate case studies, or what types of case studies could be important, where we need to dig into specifically. And then you hit the next slide. And this all goes back to, there's a very strong AI4ES idea of really being user-driven and very interdisciplinary in focusing on these different types of questions and making sure we're being good scientists and having data on these things and not just making assumptions about how or what we think people will respond to, and trying to predict those things, and instead collect data. And so this is a really big part of the AI4ES mission and what makes, I think, a really amazing institute. And with that, we're going to pause. We threw a lot of data at you for the Slido break. Any questions on those? Before Andrea actually tells you, the good details about case studies. Give people a second to breathe, check in. Let us know if you have any questions. All right. Give it 10 more seconds of awkward silence and I'll disappear.
Think you're up, Andrea.
Yeah, all right, let's move forward. And so what Chris talked about was a great way, honestly, of identifying case studies, a really nice process that, well, at least that I see as identifying case studies. And really getting a good look at the data, being comprehensive, perhaps considering subsetting the data. For AI and ML, it's especially important to look at the training data, of course, to sort of get an idea of where training might be lacking, or where it's particularly robust and things that might be dominating. So I'm going to take this a little bit, drill down a little bit closer to the size of samples where we really can't compute verification statistics very well anymore. And this is single case studies. So I want to talk about how to use cases in a robust way. And first of all, I want to talk about how to pick cases. So this is just a picture. This is my very fake tropical cyclone formation probability product here. And sort of puzzling at, so we've got some higher probabilities, some lower probabilities, just looking at these different instances and wondering what's going to be a good case to pick. So we have one signal that's coming off of the coast of Africa. It's probably an African easterly wave development, which is pretty common. We have a pretty good climatology on those types of systems. So that might be a good illustrative case for how the product does for typical types of formation setups. We've got something off the coast, the east coast of the US. This might be something that's predicted to be a little more frontal. Maybe that's more of an exception. Those are really a lot harder to predict because sometimes they don't have a lot of really deep active convection. So should I consider that? Do I want to show that? Sort of maybe the model's not doing as well, but it may be a user case that would be interesting. And then we have one over on the left side that's sort of out of the domain. So this sort of brings up hopefully all the questions that you should ask yourself as you're trying to pick cases. And this falls in line with a lot of exactly what Chris was talking about. So what is the purpose of the case study? Why am I picking the cases? What am I trying to show? And what do the users want to see? Are they representative? Are they rare? Are they high impact? And how does the model perform? So next slide. I tried to advance it myself. So one consideration to take into account when picking cases is model performance. And as Chris showed, there's a lot of ways that we can sort of look at our verification, our larger scale verification statistics to help us pick cases that we think are appropriate or important to show to users. It's important to communicate where and when the model performs well and also poorly. As far as performing well, we really want to give the forecasters a sense of where these new technologies are more applicable. And I'm using forecasters sort of generically as users right now because that's sort of my bias in that I work mostly with forecasters, but we could apply this to other entities as well. And we want to tell people where it's performing poorly because we want to make sure that they know when it may not be appropriate to rely heavily on the model. And this is something that the risk communication group is digging down into more to see how this really does impact trust and confidence. But our working thoughts on this right now are that they really do matter and they'll impact how users use the product. So for the FogNet example, we had advection fog, which was a heavy part of the training data set versus the radiation fog, which was a really small piece of the data set. So this is an example of how we can look at times when we expect the model to be good on things it's heavily trained on versus not as good for these rare events. Another aspect is to be cautious when using objective criteria for choosing cases. So you might just say, oh, we're only gonna, there's all these studies and or all these cases and we're only gonna use the statistically significant results for our new hypothesis. And these figures are from the National Academy's report on the R&R. And you can see that how the picture changes. If you only look at the statistically significant results here, you get just sort of a single line sloping upwards. But if you look at all of them, you get sort of a fanning out. So objective selection criteria, they do not guarantee unbiased results. Objective sounds nice, but it's not necessarily something that's going to keep you from having inherent biases. And so that's why it's always important to be critical and thoughtful. And of course, I probably don't have to tell you guys this, but don't cherry pick. We don't want to only pick examples that are going to make our model look good. We need to figure out a more holistic picture that we need to pick for users. And so this is a case where one case certainly isn't enough. Two cases probably isn't enough either. So you do need to pick several different instances with hopefully balancing that with keeping the number of cases as small as possible to show what you need to show. So next slide. So here is a consideration when picking cases in terms of relevance to user. And I'm going to break this up into a couple of different subtopics. So first is spatial relevance. So in a scenario, say you have a new AI tool for predicting tornadoes. And it's being demonstrated to forecasters at the Huntsville, Alabama WFO office, forecast office. So we might ask ourselves, what spatial area is most relevant to the user? And so next slide. So since we're talking about Alabama, we're looking really, and forecasters in Alabama don't forecast for the entire US. They forecast for their region, and they are of course interested in the adjacent regions as well. What we don't want to do is go into that office and show them a bunch of cases that are tornadoes in Tornado Alley or from the plains. So this is a situation this is particularly important in this case because the modes and the conditions under which tornadoes form in the Southeast are quite a bit different than those that occur in the plains. And so this is a situation where, once again, you really have to start knowing what the user does, what they need, in order to pick the right cases for the job. So next slide. So another element of relevance is temporal relevance. And I'm giving an example of, once again, a very fake AI tool that predicts the likelihood of TC genesis, which is when a tropical cyclone forms, within the next 12, 24, and 48 hours. So what types of cases would be most relevant to a forecaster if we were to pick some cases to show them? And a relevant question to ask is, what time period is most relevant to the user? And so next slide. I'm not going to make you guys answer these. It may not be knowledge to all, but National Hurricane Center forecasters make forecasts for TC formation out to 48 hours, so 2 days, and 120 hours, so 5 days. And so this is a case where it's really important to know that, because they may not have as much interest in seeing how well your model predicts cases in the next 12 or even 24 hours. They might really be most interested in that 48-hour prediction. And so that's where we can show them bulk stats that line up with 48 hours, which is one of their forecast intervals. But also when we show them cases, we really want to make sure we're showing them the relevant time period so that they can sort of connect how they would use this product to do the work that they do. Next slide. So the last one, which is sort of a loaded topic, is it interesting? Because that could mean a lot of things. So this is especially important when developing AI and machine learning models and tools specifically for forecasters. So things that can make a case interesting to users that we've learned from talking to forecasters are high impact events. So your snowstorms that shut down roads and you have lots of accidents, or the power goes out in New England or Oklahoma, or happen a lot of different places in the United States. Your high impact events like big flooding or hurricanes that have a lot of storm surge and there's a lot of destruction. Those types of cases, of course, it's really, really important to get the forecast right. And so they're going to be really interested in seeing how your model can help them with those high impact cases. Rare events with significant impacts. So I have a picture here from a paper from there was a tornado in Colorado several years ago that is called the Windsor tornado. It's pretty notorious around here. And the reason is that most tornadoes move from west to east in Colorado. And this was a case of a tornado that had a northwesterly direction of motion. And so it was extremely rare and really just did not meet the norm. And so this would be another case that it could be interesting to look at a product that maybe predicts tornado motion or supercell motion and consider showing this sort of a case if it does well. And also the real forecast challenges. So forecasters tend to have a pretty good handle on the day-to-day, and it is important to show them how your product works on those sort of routine forecast problems. But there are some forecasts that are just really hard to make. And those are the forecasts that forecasters are really going to want to know, what can this product do to help me on this case that I don't have a good handle on. And so of course they're going to be very interested in seeing cases that represent some of these more challenging forecasts of the past. Next slide. So just to sort of continue to drive on this point, so how do we find out what types of cases are most relevant and interesting to forecasters? Well, we ask them. Amy showed results of asking the forecasters what they needed in order to trust the product. And Chris and the other risk communication researchers are looking into this as well individually with forecasters. So we need to understand their needs, timelines, limitations, and workflow, and we need to ask them what they find most interesting. So, and this is where we need social science research with users throughout the entire process in order to be able to do pick the cases that are relevant to the forecasters as opposed to just interesting to us, the model developers. So next slide, and I think that's it. Okay, we have a breathing break here. So if anybody wants to put some questions in Slido, please do so now. We'll keep monitoring it for just a little bit here, and then we'll move on.
Somebody who can see the Slido screen, let me know if things are showing up.
Will do. Watching it now. I don't see anything yet. There's a good discussion, though, about rare events. Emma's kicked off, and Seth and Monty have hopped in on. So if anyone's looking for something to read, it's a good chat.
There's been great sets of discussions in the Slido. I can't see Slido anymore. For the rest of today, I'm stuck on it, can't see Slido.
It is good.
So I'll switch to turning my video on because I believe I'm next. So if we're ready,
Yes.
I will switch slides. Okay. Okay, so we're going to give a second example. We're going to do essentially a case study of case studies. I thought you would be amused about that. The idea is, so we did an example on FogNet. This is a separate, completely very different problem. This work is, I'm going to introduce the goal and then introduce sort of what we're doing and then talk about how we're using it for case studies. So the goal of the work for this is to develop a first guess front system, a first guess machine learning system that would reduce the time needed for the forecasters to generate surface analysis. So this is a picture of a surface analysis over the CONUS. I have on the next slide a picture over the larger domain. You might, we talk so much about severe weather that people are like, fronts, why do I need to know what a front is? Well, fronts are really critical to many weather forecasting tasks. So I'm assuming the meteorologists in the audience know that, but perhaps not the computer scientists. We were building on work of a former PhD student of mine, Ryan Lagerquist, and developing a machine learning system that would identify warm and cold fronts, which was what Ryan did, but then we also moved it to occluded and stationary fronts as well. And for anybody who gets really excited about this work, we have a paper that should be submitted within the next few days. So hopefully it will be appearing at some point and we will be glad to share it. So our question we wanted to do with this was, how can we build the trust with our targeted end users? Our targeted end users are forecasters who will use our product to help in real time with their task of drawing fronts in their domain. And the end user needs, I thought there was supposed to be a poll in there and it's not showing up. Anyway, this is what happens when sometimes there's multiples of us editing things. The forecasters, so that you know what our end user needs look like, the end user needs, the end users are National NCEP, the forecasters specifically from the Weather Prediction Center, the Ocean Prediction Center, the National Hurricane Center, and the Honolulu Forecast Office. And I tried, like the map that Andrea was showing of the Weather Forecast Office and where they covered, I could not find a map that showed me the different regions where all of these offices cover. However, what's interesting, since we talked about data earlier today, is I can combine two thoughts here. We did a cold front frequency climatology of all the data we had from 2008 to 2020 and just plotted it on the map. And as it turns out, you can actually see the forecast office regions. So the inner part here that is the CONUS, where this line is the WPC. They put out fronts every 3 hours. There's a line out here. I hope you can see my mouse. There's a line out in the Pacific Ocean. It stretches all the way out to the Atlantic Ocean. But over in the Pacific Ocean, that's because the OPC is doing that boundary out there. But then this specific line is because of the difference between the Honolulu Forecast Office also. But OPC, the line between OPC and WPC is because OPC only predicts fronts every 6 hours. And and WPC is putting them out every 3 hours. And then there is another line, but it's very hard to see and faint in there. But then one more forecast region, which is TAF-B. If you see this line here, TAF-B has the Gulf of Mexico. So that's what I did with these slides. How do we build trust with our targeted end users? One thing we need to do, one thing on our ideas that we might come up with is we want to explain the underlying ML model. So I explained to you who our targeted end users are. Let's talk about explaining what the underlying machine learning model is. So our underlying machine learning model is that we are using a UNet 3+. You don't need to know the details of this. I'm just explaining it the same as when Chris was explaining his FogNet. If we're going to explain it to the forecasters, what we primarily have done so far is just said we used a deep learning model. Ryan Lagerquist used a CNN that actually did a pixel by pixel prediction. So on an individual pixel basis, we decided to do a UNet approach because the UNet was much more computationally efficient, because we can actually predict the fronts over the entire CONUS and over the entire large domain relatively quickly. When we're trying to run this in real time, the other one was not going to work in real time. And so we're taking in 3D inputs of a whole bunch of meteorological variables. These are the ones that the forecasters have told us are important for them in distinguishing the fronts by hand. We give them into our UNet. The UNet, if you haven't seen them too much, is an image-to-image translator. So we get in all the meteorological variables and we have it output the probabilities of the fronts. So another thing you might want to do is you might want to say, well, you know, what's inside my model? Does the model learn what we expected? So we're going to use the XAI that we talked about yesterday. For example, this is permutation importance, grouped permutation importance specifically, to say, did it find the variables that we expected to be important to be most important? And the U-wind and V-wind, which are the two components of the wind, turn out to be the most important variables, which shouldn't be a surprise to anybody who's studied fronts, because you typically find wind changes with the fronts. And then corresponding with that, because wind follows the pressure changes, pressure turns out to be an important variable. Perhaps it's surprising and perhaps it's not. They're the ones that they didn't find important. The mixing ratio, the specific humidity, and the wet bulb temperature don't turn out to be important at all. So we explain the underlying ML model in that we give the ML model and then we peer inside it a little bit so that we can show them what's most important. Another idea that building trust with the end users, well, we might do objective verification. Objective verification, just like we showed for FogNet, is easy and doable. So here's some objective verification. In the paper, we have 20-some graphics of this. I didn't want to overwhelm you all. I just picked one graphic just to show how well the cold front versus warm front verification is working, what the CSI scores are for it. And it's showing it's working really, really well. These are different because when you're doing the predictions, you could be off by a pixel. We're using ERA5 as our analyzed data, which gets back to the question that Douglas was answering earlier. Is ERA5 data really observational data or is it simulated data? It's reanalysis data. And we realized that it could be off from what was reality. And so we're looking at a variety of distances from that reality to make sure how well it's verifying for the different distances. And you could look at, if you wanted, a table that shows you the model architecture for the different things we tried. I didn't even explain that here. And then how well they work for the different kinds of fronts. And this is one way that you could show the results, but just much like FogNet, I think if you were a forecaster, what else would you want to know? You would probably want to know a lot more about the model. So given that this is a model on case studies, what you would probably want to know is that what the case studies should be. So I have given what I've told you so far, we're going to do an exercise. Given what I've told you so far, how do I pick my case study to best improve trust and show the forecasters how the model does? I'm going to hop over to Slido. I think I stopped sharing. Do we get the poll open? Can anybody open the poll? Chris, anybody? Because I can't open the poll.
I can grab it.
Okay.
So this is 3.9, right?
Think so.
All right.
But it's not showing active for me.
It's live.
Okay. So it's actually the same question as we had before, but we're asking the same question that Chris asked before, and we want to see if your answers are going to differ. So whoever's controlling the view of the Slido, can we, yeah, thank you. And now we'll start to see what you all think. Given what you know about this domain, how do you pick your case studies? And I'm going to be very curious as this settles down, how it differs from the general question that Chris asked earlier. So far, you all want to know where it did poorly, rare events, geography, best hits. I think this is a little bit different than the one you had before so far, Chris, right? Because geography was much farther down for yours.
Yeah, geography was one of the lower ones, actually.
Right. So I'm finding it really interesting that it's showing up higher here. But it could make some sense. We'll talk about that in a couple of slides. I think worst misses was not your top. Yours was rare events, right?
I think so too. And I can also show the results of the other one too, if we want to.
I'm just finding it interesting to see how different they are. We don't have to dwell on it. We can switch over back to the slides. I think these are pretty interesting. So worst misses, people want to know where it's failing. You want to see the rare events. You want to see where it's based on geography. And then you want to see after all of the places where it's failing and perhaps the hard places to predict, you want to see how well it's doing. And like Chris before, I can't scroll down to see what the bottom ones are, but it looks like common cases. And if I remember the other poll choices, other and random, yeah, aren't showing up very much. All right, so I will switch back to slides. Sorry, Zoom is not 100%. All right. So we come back to the case studies. We're going to talk about our first pass on case studies and then sort of where we went with this. Like I said, we're doing a case study on case studies. So our first pass on the case studies that we did, we came up with some case studies and we picked some interesting cases. We thought they were interesting. They had places where it did well. They had places where it did poorly. And we just plotted the front. So what we have in these graphs is we plotted the probability of the fronts and then the human drawn fronts in the exact same color. So the probability is like the shaded map here of a cold front, it's blue. And the human drawn cold front is the darker blue, the solid blue. Same with the red, probability of warm front, then the human drawn front. And then occluded was green, sorry, stationary is green, occluded is purple. And then we also made a model that was, is there any front? And that was gray. We prototyped this particular set of case studies with a forecaster. And the forecaster said, all right, this is really interesting, but I need a lot more data and I need to be able to interact with it. So that was key. So what did we do with this? Well, we took the second step on the case studies. We tried to pick some more interesting cases to try to follow a lot of what you all said, but as we'll come into what the feedback that we got, we put it into an interactive interface. The interactive interface could show the different variables that we use to build our model. I didn't show that necessarily here. I'm showing just the fronts, but we could look at temperature and wind and, well, everything we used in the ERA. And we had the forecasters actually go into our interactive interface, which we could put the URL up for everybody. There's nothing private about that particular interactive interface. It's not live. They are just case studies. We did, I think, 9 or 10 case studies and just put them up there, and you can interact with them for the whole 24-hour period, but you can't ask for new dates. And we took those case studies and we interviewed forecasters at the Weather Prediction Center, the Ocean Prediction Center in TAFB, the Tropical Analysis Forecast Branch. We interviewed 9 forecasters. I know for computer scientists, you don't like to see n equals a small number, but for social scientists, 9 is a lot of interviews. That's a lot of hours of interviews. Just want to point that out. I'm still working on getting our transcripts done with that. So I'm going to talk a little bit about the results of these case studies here. As I said, we're doing a case study on case studies. And so what I want to say is along the lines of building trust with our end users, what we want to do is we want to do co-production. We want to work with these end users to understand their needs, to figure out what it is that they need. Well, the first set of case studies that we gave to our end user who bravely tested literally a series of PNGs realized that, okay, no way, this is not what they need. The interactive interface, actually a bunch of them really loved the interactive interface, but as it turns out, they all use NAWIPs in doing their forecasting. So eventually the system has to work inside NAWIPs before we can really do full testing. So our initial results, As I said, we had 9 interviews. I'm in the process of getting the interviews transcribed right now. I will not have those transcriptions until sometime next week. So these are just initial results. But they all said they would incorporate the model into their workflow, which was a little bit surprising to us. Actually, we expected somebody to at least be grumpy, not anybody in particular. We just assumed somebody would be like, no, I don't like this. I don't want the machine learning model. But instead, every single one of them loved it. And they like our interactive interface, but they all wanted it inside the interface they're used to. And also, it's the interface they have to draw their fronts in. So it makes the most sense for them not have to go from one screen to another. If you remember the picture that was shown yesterday, and at this point, I've forgotten who showed the picture. It might have been Andrea, about the forecasters and how many windows and monitors they have. Adding one more window is just a lot more to overload. We were curious about whether or not they liked the fronts that actually said, this is a cold front, this is a warm front, versus the ones that just said, this might be a front of any type, because they had actually suggested that we train that in the beginning, and it turns out they all like the labels. None of them like the fronts, no fronts. It was okay, but if we asked them to prefer it, they all preferred the labeled ones. Perhaps not surprisingly, but I want to point this out because it matters for machine learning. Every single one of them preferred probabilistic guidance over deterministic guidance. But for the point of what we're talking about here, the forecasters wanted to see case studies over their specific domain. So they wanted to see where they struggle by different office. Remember, we interviewed forecasters from WPC, OPC, and TAFB. We tried to get a hold of Honolulu, but we did not succeed. But the forecasters had different areas that they struggle. And if we, the humans, hadn't been working with them to figure out where the case studies should be, we, in our case studies that we put onto the domain for them to study, we just took things we thought were interesting. It turns out that there were very specific geographic regions. I was waiting to see if you all picked geographic regions on your poll. There were very specific geographic regions that differed by domain. The WPC cares about one part of the geography versus the TAFB versus the OPC that really matter. The other thing I wanted to point out, just because it's kind of fun and it's a little bit aside from the case studies, but it was very interesting. Sometimes the machine learning and the forecaster fronts that were given to us, which were given to us from fronts that were drawn in real time from 2008 to 2020, sometimes they would disagree. So the machine learning would say there was a front and the forecaster originally had not drawn a front. And we discovered that, in fact, in almost all of those cases, the forecaster would look retrospectively at it and say, yeah, there should have been a front there. And so one of the other key takeaways out of all of this data, because it goes back to our data workflow, is that the data is not going to be perfect. The forecasters are working on tremendous time pressure. The WPC forecasters have to issue fronts every 3 hours over the whole CONUS, right? They're going to make mistakes. And if you aren't taking that into account when you're doing your training, you might be making some mistakes, which brings us back to our data. But I'll bring us back to case studies. So in our case study choices, our forecasters checked what happened in the main part of their domain, right? They wanted to see, when you all were answering the poll, you were asking, they wanted to see how well it worked. They definitely wanted to see how it worked in their main part of the domain. Like CONUS, they just looked across the whole CONUS, right? And then they would focus on the very hard parts of their domain. So TAFB very specifically had a very strong request that they wanted to look at how fronts come over the Mexican mountains. Because apparently when they come over the Mexican mountains, they aren't as well sensed and they tend to break up, and they wanted to make sure that our model was behaving correctly as those fronts were passing over the mountains. WPC wanted to look at the upper part of Canada because they're responsible for CONUS, but they're also responsible for the upper part of Canada. And again, it's not as well sensed, and they wanted to see how the fronts were handled up there. And then they also wanted to see the fronts as they hit the Pacific coast, because if you remember the map from a couple of slides ago, they do part of the Pacific coast. And that part, as it hits the Pacific, they tend to do things when they hit the Pacific mountains. And they wanted to see if our model was able to handle that. And then OPC, the forecasters immediately jumped in and said, oh, this part of the area is not sensed very well. And they wanted to look at how well we handled the poorly sensed parts of the Pacific and the Atlantic. And that was really interesting to us because as we're putting together our model and trying to increase the trust so that this actually becomes a operational model, all of this work on the fronts, by the way, is funded by AJETI, NOAA-JETI, which is the Joint Technology Transfer Initiative, which means that it should become an operational model. If we want it to become an operational model with our forecasters, we really need to enhance the trust, and they need to see the pieces that they care about most and not the pieces that we thought they should care about. So I think we're hitting time right on time. What we're going to do for the end of this is try to talk about sort of general advice on how to do case studies. So for example, provide case studies in their main area of use, like we just talked about, you really do need to know that the machine learning product works for the majority of the cases. If you don't work for the majority of the cases, then who really cares how well it works for the edge cases? Because if you can't use it 80 or 90% of the time, then it's probably not going to get used. But you don't need to focus your case studies in that main area of use. You have enough of them to say, okay, here's my objective verification. Here's some examples of the case studies in the main area. But now we need to look at, some of these edge cases that we just talked about. Also, we really need to know where it's going to break. One of the forecaster interviews quotes that I really wanted to share is that Forecaster 5 says, if you're saying trustworthiness of a certain product, it would be how well does it perform on a consistent basis? No model is ever going to be perfect. There are a couple other quotes that are related to this, but they were already given on day 1 and day 2, so I didn't want to repeat them. The forecasters know that the models aren't perfect. No NWP model is perfect. So why should they expect the machine learning model to be perfect? They go into it with the expectation that the machine learning model is not going to be perfect. And I think sometimes we machine learning developers think, oh, we should make this model work all the time. They know it's not going to work all the time. What they want to see is how it breaks, where it breaks, and under what conditions it breaks, right? So that you can know it's going to work everywhere but the Mexican mountains. Okay, I'm going to have to do the mountains over Mexico by hand, right? Maybe that's the first model, and then the next version we try to fix the Mexican mountain problem, right? I mean, just giving an example. I'm not saying our model doesn't work over the Mexican mountains, although I will tell you that the Rocky Mountains do provide some interesting challenges just due to data model levels. So you need to work with your end users to identify the challenging scenarios, right? Because as I said in the previous slide, we went into it with a set of what we thought were interesting scenarios, and we found out that our end users had very different scenarios that they wanted to look at that we hadn't even thought about. We literally had not thought about how the fronts interact with the Mexican mountains or the Pacific coast mountains, or how it worked, in very sparsely sampled areas of the ocean. We just hadn't thought that that would be the most interesting things. You need to focus your case studies on those challenges for the end users. Look at the boundary cases, look at the edge cases, look at the rare events. We had some very specific requests from our forecasters. They were hoping we could do it in real time. Unfortunately, since we're using ARA5, we can't do anything in real time. But they wanted to know very recent rare events that had come in. So for example, we were doing these interviews in the winter, in the early spring, and they were asking about that cold front that dipped down all the way down into Texas. And they wanted to see how well it had worked on that. And then finally, look at the well-known trouble spots. I can't tell you how many forecasters said, well, this area provides problems for me, so I would really like to see if the model could help me with that, right? And so if you can identify those well-known trouble spots in whatever it is you're trying to predict, I think that's a good place to put in some case studies, because then they could know it could help them or not. So we're going to ask another couple of questions. We're going to make sure that we're waking you up towards the end of the day. How do we do a case study if we don't know the right answer? And that's going to be the questions over in Slido. Before I pop over to Slido and switch screens, I want to give you a little bit of thought on this. I'm switching a little bit from fronts. I've sort of ended my case study on fronts. And I want to think about climate, for example. How do we do a case study on climates when we don't know what the future is going to be, right? Can we verify in the past? Does that provide enough evidence? What do you do when there are really no comparisons out there? There is nothing. How do we compare to the next 100 years? We got to wait 100 years. And the real question out of all of this, can a case study with no known truth, that is something that's doing a case study of what it's going to look like 100 years from now, improve trust? And with that, I will stop sharing me, and let's hop over to the Slido share. Choose cases to compare models. Oh, okay. Think about that. So you have multiple models and you want to use case studies just to see how the different models give you different answers. That's a good one. I'm looking forward to all these answers coming in. Treat it as a hypothesis. Learn from there. The right answer is subjective based on human excerpts. Simulate realistic cases. Yes, well, I mean, that's kind of what we're doing with the models. The question is, how realistic are they? Assess if the answer is at least physically consistent. Good point. Yes, so if we're making a case study for the future, we want to make sure that it's at least not lost its mind. You got to start somewhere. If you don't know the right answer, I guess this one will be the first one, and then you do another one to compare to your first. It's a good start. Ensembles with different cases. I think that gets to the answer we had in the beginning of using different models. Perfect model studies using synthetic data, that's good. XAI, I like somebody's bringing in the XAI. Use synthetic training data, so very similar to the one we just had. Start with real world cases we care about the most. Look at the past. Yes, Yes, we can look at the past, but sometimes if the past is part of your training data, then the case study isn't necessarily as meaningful, right? If you're trying to predict the future. This is going by quickly now. See if you can bound the worst case scenarios. Use different models. That comes back to the beginning one. I like that as an answer. Douglas, you stuck one in chat and Zoom, but nobody can see your chat and Zoom, so stick it in Slido. There, you just did. Thank you. Work with the users to identify use cases. I like that. So make sure that you're working with your end users and what they care about. I'll give it another minute here and then we'll hop back over because we're almost out of time today. So we'll make sure we get through the last few slides. By the way, while you all are typing, we're archiving all of these. And at the end, we're going to go through all of the answers because we're finding what you all are typing so fascinating. And we want you to know that even if I didn't get to your answer before we switch back, that we're still looking at them, okay? So I appreciate all of it. And yes, I agree, this is very tricky. On that note, I'm going to switch back because I realize I only have 11 minutes. And I think if I recall correctly, there might be one more poll. I can't remember. Okay. Yeah, see, I thought I had a second poll. Chris, do you think we have enough time to do the second poll and still get through the remaining slides?
Yeah, I think we got,
okay.
We still have 10 minutes.
Okay. So the second question, how can we use the idea of case studies to improve understanding of the risk and trust in future predictions? And I grabbed from a paper that I only just learned about last week from the risk communication team. There's a recent paper that came out. It's not anybody from the TAI4ES. The citation for the paper is right there. It's called Climate GAN. And it's a model that can predict future. It can try to take in images of the current time and give you a picture of what it would look like under a climate disaster. So the picture that's shown here is a model that simulates extreme floods. So on the right, there's an extreme flood at Mila, and then on the left is what it really looks like. And I found this paper really interesting because I wanted to see, you could use this as case studies as a way to try to improve understanding of the risk and trust in the future predictions. This is, but there might be some really interesting ethical challenges involved in this. So go ahead and open the poll, whoever's running the polls, and we'll hop over to there in a second. Are there ethical challenges involved in presenting these hypothetical things? Oh, I was going to keep reading the slides, but that's okay. There was one more question on the slide. I'll hop back over to it myself. How does the hypothetical AI generated scenarios impact trust was my remaining question. And we'll come back to there. It makes the results relatable, something they can visualize with their own context. Yes, I like that. But then we get into these really interesting ethical scenarios. That's the part I was very curious about. It tells a story. I agree. And I think that somehow this story, I mean, if you look at this and you think, what does a 1 in 1,000-year flood look like? And what happens if this 1 in 1,000-year flood happens 1 in 50 years or 1 in 20 years? You still don't know what it looks like until all of a sudden you look at the flood. Are we just going to show people's houses? Yes, in fact, Climate GAN did that. They used Mila because that's where they're headquartered, but you can use their model to just show what it's going to look like when your house is flooded. Yes, and there's the question I was looking at. How does this handle trust? Right, we've now developed this model. We can show you what your house would look like under a flood. Do you trust it? And how do you use this model to improve trust? And how do you know that this could help you with case studies? It's kind of a hypothetical case study. So you need to understand what it means. Case studies are a mode of communication that can be used in conjunction with other ways of communicating risk and building trust. Yes, so this is another mode of communication. Are we just going to show rich people's houses? I hope not. I hope we're showing everybody's houses. And then the next question, the model does poorly or a scenario doesn't verify. Right. That picture that showed the impact on Mila doesn't necessarily mean that the flood is going to look exactly like that if it floods Mila. Right. And so the question is, what does it do to help you with your communication and your understanding of that? Let's see, help demonstrate how bad the model could be in the worst known failures and help put a bound on how poorly things might go if the prediction is wrong. That's a good one. Yes, and particular use to those in leadership. So you could say, this is what it could look like, and this is how good it could. And I like the drawing attention to the risk. I think some people really, especially if we get to the not just rich people's houses, if we show the flood risk for everybody, if everybody could say, this is what my house is likely to look like sometime once in the next 20 years, it might be more interesting than if they just have a concept that it might get 10 inches of rain, and what does that mean for them? 10 inches of rain in 2 hours. In the nature of time, I'm going to hop back over to my slides. So looking at just a few other case study open questions as we're just wrapping up, how can we connect what we've just done in case studies with XAI and interpretability? So one thing that we could do is we could use these case studies to connect with an explanation. So you get you get both a local view and a global view, right? The XAI was more of a local view. You could do a case study and get a global view across sort of a set of cases. And then also when we were asking you about how to pick cases, this is an example of some work with Ryan Lagerquist, where we were looking at how well a method did at predicting tornadoes. What we did is we looked at all 4 parts of the contingency table: best hits, worst false alarms, worst misses, best correct results. And he did a probability match mean estimate for the top 100 of each of these, and then plotted them to make sure that what came out actually made sense. And that helped because, sorry, I have the hiccups now. For example, the best hits looked relatively like a tornadic storm. If you hallucinate a little bit, it might even be a hook echo. You kind of have to squint, I admit. But if you look at best hits and best correct nulls, you can see that there's nothing in the best correct nulls. And then we went to examine the worst false alarms, for example, and we found out that over 70% of the worst false alarms were actually warned by the human forecasters. So they missed them too. So those case studies turned out to be really interesting. And this was a different kind of case study than anything else we've talked about so far because they were aggregated case studies. We did individual cases and then we aggregated them into one graphic for a mean case study. Another thing we could do to connect the case studies with XAI and interpretability is we could generate synthetic examples. This is also work from Ryan Lagerquist. It's not yet in a paper, so you'd have to go look at his PhD thesis to find it. But here we used backwards optimization, which is an XAI method that we did not talk about yesterday, but where you take the output of the model, you give it some input, and then you optimize backwards to maximize some probabilities. So he did 2 different ways of doing that. He took tornadic images and optimized them to be non-tornadic, and then he took non-tornadic images and optimized them to be tornadic, so that you could sort of see what an optimal tornadic input could look like. It's a very interesting set of results, and in the nature of staring at my time, I don't think that we're going to get through much more discussion, but I'll be glad to tackle some Slido on it. One other paper I want to reference to you, this is from Emma Eberdupoff, who talked yesterday, and I believe is going to be talking again tomorrow. So this is a paper looking at how you could do a workflow using case studies in XAI. So here we have a sample workflow that helps you construct your sets of samples, generate your hypotheses, and test your hypotheses. And in the first part, you want to figure out what samples you want to focus on. And so here's some strategies that you might want to look at. Biggest successes and failures, like we've talked about, grouping by a class, grouping by some meteorological property, like we talked about with geography, clustering your input samples, creating synthetic samples. There are all of these things you could do. And then you run them through the neural network. Don't really need to talk about much of that. You look at what's happening, what the neural network has done. You might look at your XAI tools, LRP, whatever the favorite CHAP, whatever it is. You look at your performance measures, and then you're going to construct some hypotheses. And you want to say, how well do these results work? You have your meteorological experts interpret them. And then as needed, you might need to test this. You might need to change what has happened. You can select or construct a new set of examples and predict what you should see, make sure you're correct. Do this in a cycle so that you know that what you're doing with the XAI and the case studies and all of that is very scientifically done. You're not just cherry picking. This gets back to the statement that Andrea made earlier. We really don't want to just pick an example that meets a specific, like it did a great job. Or maybe you don't want to pick an example of how it failed most spectacularly. You don't want to cherry pick either way. You want to understand scientifically what you think it's going to do. This will help increase trust because you have a theory about what it's going to do. You do the case study, you look at it, and you see that it does it. So this brings us back to Chris's diagram from the beginning. Sort of where do we go from all of here? We work to increase the trustworthiness today of our data and our workflows. We want to make sure we're clearly communicating limitations in the data and workflows. I want to make sure we're doing co-production with our end users and our social scientists throughout the whole process. And we want to communicate constraints and fail-safes and ways that our data works, ways that our model work, and ways that our model fails. And my breathing break is just, I'm going to check the Slido questions, but before I check these Slido questions, I'm going to point out, I think at the very end I have the agenda. This was the end of today. We're going to go check the Slido questions in a second. I want to thank everybody who's been helping us, the multimedia team especially, because they're getting things running smoothly in the background and you all don't see them, but they are doing a great job in the background. And while I wait for Slido questions to come in, this is my last slide, and then I'll pop over to Slido. Just remind you of what's going to happen tomorrow. Tomorrow is going to be all about uncertainty communication, and I think it's going to be great. I think it's going to be great. I'm going to quantify my uncertainty. I know it's going to be great. I'm going to switch over to Slido and see if there are any questions. All right, so Chris, you've been monitoring this. Are there any that need to be desperately answered? Because I think the top one has been discussed, I'm pretty sure.
Yeah, I think that everyone's gotten a reply so far. You got a shout out for a nice approach. We got a nice little smiley face at the end. And then just people interested in some more of the questions, if we can post them.
Okay, so what we'll do with the Slido is we will try to answer anything else that's left. And then we will see you all tomorrow. So we are really happy with all of your interaction, and I'll see you all tomorrow. Thank you.